Hello there. Tonight, we are leaving behind the bright galaxies, the crowded stars, and the familiar corners of the universe humanity has spent centuries trying to understand. Because far beyond the glowing rivers of the cosmos, there are places so empty, so silent, that even light itself seems lonely there. Vast cosmic voids, ancient regions stretching across hundreds of millions of light years, where entire galaxies drift alone through endless darkness. No nearby neighbors, no crowded star systems, just silent islands of light floating in the greatest emptiness the universe has ever created. And the strangest part of all is that these forgotten galaxies may hold the answers to some of the biggest mysteries in existence. Dark matter, dark energy, the expansion of the universe, and perhaps the fate of everything. Tonight, you're going to travel into the loneliest regions ever discovered by humanity. You will witness galaxies that should not exist, hidden structures woven through invisible darkness, and ancient light from the Big Bang itself crossing silent oceans of empty space. So dim the lights, settle in, and let the universe slowly pull you away from Earth. But before we begin this journey into the void, if you truly enjoy calm explorations of space, science, and the deepest mysteries of the cosmos, take a moment to subscribe to the channel and gently leave a like on this video. It helps this channel continue creating these long, peaceful journeys through the universe, night after night. Now, take a slow breath, relax your mind, and prepare to drift into the silent darkness between the galaxies. Chapter 1. The Silent Oceans of the Cosmos. Far beyond the bright spiral arms of familiar galaxies, beyond the glowing clusters that fill astronomy photographs with rivers of stars, there are places in the universe where almost nothing exists at all. These immense regions are known as cosmic voids. To the human mind, they're difficult to imagine. Even ordinary space already feels empty beyond comprehension. Yet cosmic voids are emptier still. They're the vast, silent oceans between the great islands of matter in the universe. Some stretch across hundreds of millions of light years, containing only a handful of galaxies drifting through darkness, so complete that even neighboring galaxies may lie tens of millions of light years apart. And inside these lonely regions live some of the strangest galaxies ever discovered. Astronomers call them void galaxies. For decades, scientists once believed galaxies could only properly form in crowded regions of space, where gravity pulls enormous clouds of gas together like invisible rivers flowing toward giant cosmic cities. Yet the universe had other ideas. Hidden deep within these quiet expanses, researchers began finding isolated galaxies quietly evolving in almost complete solitude. The discovery changed the way scientists think about the structure of the cosmos itself. One of the first surprising facts about void galaxies is that many of them appear unusually youthful. While galaxies in crowded clusters often collide, distort, and age through billions of years of violent interactions, void galaxies can remain relatively undisturbed for astonishingly long periods of time. Some continue forming new stars at rates that seem unexpectedly active compared to their lonely environments. In a way, they're cosmic time capsules. The universe itself is not arranged randomly. On the largest scales, galaxies form something called the cosmic web, a gigantic structure made of filaments, clusters, and nodes stretching across unimaginable distances. Between these glowing filaments lie the voids, enormous bubbles of near emptiness. If humanity could somehow step outside the observable universe and look inward, the cosmos might resemble a three-dimensional sponge or foam, with galaxies lining the thin surfaces and edges, while vast hollows remain mostly dark. These voids are not small. The famous Boötes void, discovered in 1981, is one of the largest known empty regions in the observable universe. It spans roughly 330 million light-years across. To understand that scale, consider this. If the Milky Way were reduced to the size of a grain of sand, the Boötes void would still be larger than entire continents on Earth. Yet even inside that enormous emptiness, galaxies still exist. They drift quietly through the darkness like isolated lanterns floating across a frozen sea. Astronomers have learned that void galaxies often behave differently from galaxies living in crowded regions. Many possess higher amounts of hydrogen gas, the raw material used to create stars. Because they experience fewer galactic collisions, they sometimes maintain elegant spiral structures for longer periods. Some rotate in strangely pristine ways, almost untouched by the chaos common elsewhere in the universe. One particularly fascinating fact is that void galaxies may help scientists understand what the early universe looked like billions of years ago. In dense galaxy clusters, gravitational interactions constantly reshape galaxies. They merge together, strip gas from one another, and trigger massive bursts of star formation. But void galaxies often evolve more slowly. Their isolation preserves conditions that may resemble ancient cosmic environments from long ago. Studying them is like examining fossils preserved deep beneath untouched layers of stone. And the deeper astronomers looked into these voids, the stranger things became. In 2012, researchers studying a void galaxy known as Markarian 177 noticed something extraordinary. A nearby quasar, one of the brightest objects in the universe, illuminated enormous hidden streams of gas surrounding the galaxy. This revealed that even in the emptiest regions of space, invisible rivers of matter still flow quietly through the darkness. The void was not truly empty after all. In fact, cosmic voids contain dark matter, faint hydrogen gas, radiation, and invisible gravitational forces threading through space itself. The emptiness is only relative. Another remarkable detail is that sound, as humans understand it, cannot travel through space. Yet astronomers sometimes describe voids as silent for another reason. Galaxy clusters are crowded, energetic environments filled with radiation, magnetic interactions, and intense activity around black holes. Voids, by comparison, are places of extraordinary calm. Star formation rates are often slower. Supermassive black holes appear less active. Gravitational disturbances are weaker. In many ways, void galaxies live quieter lives. This calmness creates some unexpectedly beautiful structures. Certain void galaxies possess immense extended disks of hydrogen gas reaching far beyond their visible stars. Others contain faint blue populations of newly formed stars glowing softly against the darkness. Because they encounter fewer neighboring galaxies, delicate structures survive for billions of years without being torn apart. Some scientists even suspect that void galaxies may rotate differently due to the large-scale geometry of the cosmic web surrounding them. Early observations suggest that galaxies inside filaments tend to align with the structure of the web itself, while galaxies inside voids may show more unusual orientations. It is as though the shape of the universe subtly guides the spinning of entire galaxies. The idea sounds almost poetic. The architecture of the cosmos influencing the dance of stars. Another curious fact is that void galaxies are often smaller than galaxies in dense clusters. Many are dwarf galaxies, containing only a fraction of the stars found in the Milky Way. But not all of them are tiny. Some are surprisingly massive spirals, existing in places where astronomers once believed such galaxies should be nearly impossible to form. One example is the galaxy known as UGC 1382. For years, astronomers mistakenly classified it as a small, ordinary galaxy. But deeper observations revealed a gigantic faint disk surrounding it, stretching more than 700,000 light-years across, over 7 times wider than the Milky Way. It turned out to be one of the largest known spiral galaxies ever discovered, quietly hidden in a low-density environment far from crowded galactic regions. Its discovery challenged existing theories about galaxy growth. How could such a massive structure develop in such isolation? Scientists now think that void galaxies may grow gradually through slow accretion, gently collecting gas from surrounding space over billions of years instead of violently merging with neighboring galaxies. In crowded galaxy clusters, fast interactions dominate evolution. In voids, patience shapes the cosmos. Time behaves differently there. And then there is the mystery of dark matter. Galaxies rotate so quickly that visible matter alone cannot hold them together. Some unseen mass must provide additional gravity. This invisible substance, dark matter, forms gigantic halos surrounding galaxies and stretching throughout the cosmic web. Void galaxies offer researchers unique laboratories for studying dark matter, because their isolated environments reduce the confusing effects caused by neighboring galaxies. Some simulations even suggest that tiny invisible dark matter filaments may run through voids like ghostly spider silk. Along these hidden structures, faint dwarf galaxies could quietly form where almost nobody expected them to exist. The more scientists study voids, the more they realize the universe dislikes true emptiness. Even the darkest regions still contain structure. Light itself behaves strangely inside cosmic voids. As photons travel across these enormous underdense regions, gravitational effects slightly alter their energy. This contributes to a phenomenon called the integrated Sachs-Wolf effect, where ancient light from the Big Bang changes subtly while passing through giant voids. By measuring these distortions in the cosmic microwave background, astronomers can learn about dark energy, the mysterious force causing the expansion of the universe to accelerate. So in an extraordinary way, studying empty space helps scientists investigate the ultimate fate of the cosmos. The voids are not merely gaps between galaxies. They are active participants in the evolution of the universe itself. One especially relaxing thought emerges from all this cosmic emptiness. If humanity somehow traveled into the center of a giant void, the night sky would appear profoundly different. Instead of thousands of visible galaxies filling deep space telescopes, there would be far fewer bright structures nearby. The heavens would feel darker, quieter, and lonelier than anything humans have ever experienced. Entire civilizations living inside a deep cosmic void might struggle to discover the true scale of the universe because fewer galaxies would be visible around them. Some scientists have even wondered whether intelligent life inside extreme voids could have developed completely different cosmological theories, simply because their skies reveal less information. Their universe would appear smaller, more isolated, more silent, and yet perhaps more mysterious. Because in the deepest darkness of the cosmos, the universe still whispers its secrets softly through drifting galaxies, hidden rivers of gas, invisible matter, and ancient light crossing billions of years of time. Void galaxies remind humanity that even emptiness contains wonder. Even silence contains structure. And even in the loneliest places imaginable, stars continue to shine. In the vast architecture of the universe, cosmic voids are often compared to deserts. But even deserts on Earth contain winds, shifting dunes, hidden life, and traces of ancient rivers beneath the sand. In much the same way, the emptiest regions of the cosmos are far more dynamic than they first appear. Void galaxies drift through environments so thinly populated that every faint glow becomes precious, every star-forming cloud becomes unusual, and every gravitational interaction becomes a rare event measured across millions of light years. One of the most fascinating discoveries about void galaxies is that many of them continue forming stars long after astronomers expected their activity to slow down. In dense galaxy clusters, galaxies often lose their gas through violent encounters. As galaxies pass near one another, enormous gravitational forces can strip away clouds of hydrogen like storms tearing leaves from trees. Without hydrogen gas, star formation gradually fades. But inside cosmic voids, galaxies are spared much of this chaos. Their reservoirs of gas can survive for extraordinarily long periods, allowing them to continue quietly creating young blue stars deep into cosmic history. Some void galaxies almost appear rejuvenated compared to their crowded counterparts. Astronomers studying these isolated systems have repeatedly observed high levels of neutral hydrogen gas using radio telescopes. In some cases, the gas disks surrounding void galaxies extend far beyond their visible stars, forming faint invisible halos stretching across enormous distances. These hidden structures are detectable only through radio observations, revealing that galaxies are often much larger than human eyes alone can perceive. One remarkable example is the galaxy KK 246, sometimes called the local void galaxy. It exists within a particularly empty region known as the local void, near the outer boundaries of humanity's galactic neighborhood. KK 246 appears highly isolated, yet it possesses an extended gas disk and continues actively forming stars. Its lonely existence challenges older assumptions that galaxies require crowded environments to thrive. The local void itself is an extraordinary place. It lies adjacent to the local group, the galactic neighborhood containing the Milky Way galaxy, the Andromeda galaxy, and dozens of smaller galaxies. Astronomers estimate that the local void spans hundreds of millions of light years and contains far fewer galaxies than average regions of the universe. Interestingly, the Milky Way may actually be moving away from this emptiness due to gravitational effects created by surrounding matter concentrations. In a strange way, emptiness itself influences motion. Gravity pulls galaxies toward dense regions, but the lack of gravity inside voids also creates an outward effect. Scientists sometimes describe voids as pushing galaxies away, though technically it is the stronger pull of surrounding structures doing the work. The result is a cosmic dance shaped equally by presence and absence. Another surprising fact is that temperatures inside cosmic voids can become extremely low compared to denser cosmic regions. Although space everywhere is cold, galaxy clusters often contain vast clouds of superheated gas reaching millions of degrees due to constant collisions and energetic activity. Voids lack much of this heating process. Their sparse matter means less friction, fewer collisions, and lower overall energy densities. These are among the quietest thermal environments in the universe. Yet they are not completely dark. Even the emptiest voids are flooded with ancient radiation left over from the Big Bang. This faint afterglow, known as the cosmic microwave background, fills all of space uniformly. Every void galaxy exists bathed within this ancient light, receiving photons that have traveled nearly 13.8 billion years across cosmic history. It is a calming thought. Even in the loneliest corners of existence, the oldest light in the universe still arrives faithfully. Astronomers have also discovered that void galaxies often possess unusually delicate shapes. Spiral arms can remain thin and well-defined because fewer galactic encounters disturb them. In crowded clusters, gravitational interactions twist galaxies into distorted forms, trigger bursts of chaotic star formation, and sometimes completely destroy spiral structures. But void galaxies may preserve elegant rotational patterns for billions of years. Some researchers compare them to untouched ecosystems evolving in isolation. This isolation may even affect the chemical composition of stars inside void galaxies. Because fewer generations of stars have exploded and enriched the surrounding gas with heavy elements, some void galaxies appear chemically primitive. In astronomy, elements heavier than hydrogen and helium are called metals, even when they include oxygen or carbon. Younger or less evolved galaxies often contain lower metallicities, providing clues about how the first galaxies in the early universe may have behaved. In other words, studying void galaxies can sometimes feel like looking backward through time. Among the more mysterious observations are galaxies found almost exactly in the centers of giant voids, where astronomers once predicted almost nothing should exist at all. According to computer simulations of cosmic evolution, matter naturally flows outward from underdense regions toward denser filaments and clusters. Over billions of years, void centers should become increasingly empty. And yet some galaxies remain there. Why they formed or survived remains an active scientific puzzle. Certain theories suggest that tiny fluctuations in dark matter density allowed isolated pockets of gas to collapse independently long ago. Others propose that small hidden filaments may thread through the voids, providing faint pathways for galaxy formation invisible to current instruments. Dark matter itself remains one of the greatest mysteries connected to cosmic voids. Scientists estimate that ordinary visible matter makes up less than 5% of the total universe. The rest consists primarily of dark matter and dark energy, invisible components that shape the cosmos on the largest scales. Void galaxies allow researchers to study how dark matter behaves in environments largely free from the complicated interactions common in galaxy clusters. Interestingly, some observations hint that voids may contain slightly different dark matter distributions than predicted by certain cosmological models. This has led scientists to test alternative theories about gravity, particle physics, and cosmic evolution. Even tiny discrepancies inside voids can provide important clues about the deeper laws governing the universe. The emptiest places may hold the biggest answers. Another deeply fascinating phenomenon involves the expansion of cosmic voids themselves. As the universe expands, voids tend to grow larger over time. Matter gradually drains away from underdense regions into surrounding structures, causing voids to widen like bubbles, slowly inflating within rising bread dough. Computer simulations show that the universe has become increasingly foamy across billions of years, with voids expanding and filaments sharpening into enormous interconnected networks. This means the large-scale structure of the cosmos becomes more pronounced with time. The rich regions grow richer. The empty regions grow emptier. And through this slow evolution, void galaxies continue drifting quietly across immense darkness. Some astronomers believe supervoids, exceptionally gigantic voids, may even influence observations of the cosmic microwave background. One controversial example is the so-called cold spot, an unusually cool region in the background radiation discovered by satellite missions studying the early universe. Some researchers propose that an enormous supervoid lying between Earth and the cold spot might partially explain the temperature difference by altering photons traveling through it. Though the debate continues, it highlights how even empty space can shape the light crossing the universe. Void galaxies also reveal something beautiful about cosmic survival. In crowded galaxy clusters, mergers are common. The Milky Way itself will eventually collide with Andromeda billions of years from now, transforming both galaxies into a new, larger system. But many void galaxies may never experience major mergers at all. Some could remain structurally stable for astonishing spans of time, evolving gradually and quietly while the rest of the universe undergoes dramatic collisions. There's something deeply peaceful about that idea. Entire galaxies living slow, undisturbed lives in silent regions untouched by cosmic violence. Astronomers using powerful observatories like the National Radio Astronomy Observatory and the European Southern Observatory continue searching these lonely regions for new surprises. Advanced sky surveys have revealed thousands of void galaxies, yet researchers suspect many more remain hidden due to their faint brightness. Future telescopes may uncover entire populations of ultra-dim dwarf galaxies drifting invisibly through these regions. And perhaps most intriguingly, voids may help scientists understand dark energy itself. Dark energy is the mysterious phenomenon accelerating the expansion of the universe. Although nobody fully understands its nature, cosmic voids are highly sensitive to its effects because their growth depends strongly on the universe's expansion history. By carefully measuring how voids expand and evolve, astronomers hope to refine models explaining why cosmic expansion continues accelerating billions of years after the Big Bang. So the study of emptiness may eventually explain the destiny of everything. In the end, void galaxies remind humanity that the universe is not defined only by brilliance and activity. Some of its deepest truths emerge from stillness. Between the crowded galaxy clusters and blazing quasars lies a quieter cosmos, one shaped by isolation, patience, and slow evolution unfolding across unimaginable scales. These lonely galaxies drift through darkness, carrying billions of stars within them, preserving ancient conditions, revealing hidden physics, and illuminating mysteries surrounding dark matter, dark energy, and the structure of space-time itself. Far from being meaningless gaps, cosmic voids are essential pieces of the universe's design. They give shape to the cosmic web. They influence motion across hundreds of millions of light years. They preserve galaxies that might otherwise never survive. And somewhere inside those immense, silent oceans, beneath skies darker than any human being will ever witness, stars continue glowing softly in the endless night. Chapter 2: Galaxies that should not exist. In astronomy, there are discoveries that quietly expand human understanding. And then there are discoveries that leave scientists staring at their data in disbelief. Void galaxies often belong to the second category. For many years, astronomers believed the universe followed a relatively straightforward pattern. Dense regions of space produced large galaxies because gravity gathered enormous amounts of matter there. Sparse regions, meanwhile, were expected to remain mostly barren, too empty for significant galaxies to form properly. The logic seemed reasonable. Galaxies require matter, gas, dark matter halos, and billions of years of gravitational accumulation. If a region of space contained very little material to begin with, then large galaxies should be extremely rare there. Cosmic voids were expected to contain only a few tiny dwarf galaxies, quietly scattered across enormous darkness. But the universe rarely obeys human expectations completely. As telescopes improved and sky surveys became more detailed, astronomers began finding galaxies inside voids that appeared far too large, too active, or too organized for their lonely surroundings. Some possessed enormous spiral disks. Others formed stars at surprisingly high rates. A few seemed almost untouched by the violent galactic evolution common elsewhere in the cosmos. They looked like galaxies that should not exist. One particularly mysterious category is known as low-surface brightness galaxies. These galaxies are so faint that they can become nearly invisible against the darkness of space itself. Unlike bright spiral galaxies packed with luminous stars, low-surface brightness galaxies spread their stars thinly across enormous distances. Some are ghostly giants, larger than the Milky Way, but containing far fewer visible stars. For decades, astronomers missed many of them entirely. The night sky, paradoxically, can hide extremely faint galaxies more effectively than bright ones. Traditional surveys focused on luminous structures, meaning entire populations of diffuse galaxies may have gone unnoticed for generations. One famous example is the galaxy Malin 1. Discovered in 1986, Malin 1 stunned astronomers because of its extraordinary size. Its faint disk stretches roughly 650,000 light-years across, making it one of the largest spiral galaxies ever identified. Yet despite its gigantic scale, it remained hidden due to its extremely low brightness. Even more surprising, galaxies similar to Malin 1 seem more common in low-density environments like cosmic voids. Scientists still debate exactly how such enormous structures form in relative isolation. One theory suggests these galaxies grow slowly over billions of years through gentle gas accretion rather than repeated violent mergers. Another proposes that unusual dark matter halos stabilize their vast disks, preventing collapse or disruption. Either way, they challenge traditional models of galaxy formation. Another strange fact about some void galaxies is their color. Galaxies in crowded clusters often appear reddish because older stars dominate their light. Younger blue stars burn brightly but live relatively short lives, so galaxies that stop forming stars gradually redden over time. Yet many void galaxies appear unusually blue, indicating ongoing star formation despite their isolated environments. This means they continue creating new generations of stars long after many cluster galaxies have become quieter and older. Astronomers studying these blue void galaxies discovered something fascinating. Their gas supplies often remain remarkably undisturbed. In dense clusters, galaxies lose gas through gravitational stripping and collisions. But in voids, gas reservoirs survive much longer, allowing slow but continuous star formation across billions of years. Some void galaxies almost seem preserved in cosmic isolation chambers. And then there are ring galaxies. A few isolated void galaxies display enormous ring-like structures formed by unusual gravitational interactions. Normally, ring galaxies emerge when one galaxy passes through another, triggering outward-moving waves of star formation. But finding such structures inside sparsely populated voids raises difficult questions. Where did the interaction come from? Did hidden dwarf galaxies once pass nearby? Were ancient collisions far more common in the early universe than previously believed? Or could entirely different mechanisms produce these strange forms in isolated environments? Astronomers continue searching for answers. One of the most fascinating cases involves a galaxy called NGC 6503, located near the edge of a large cosmic void, sometimes referred to as the local void. Though relatively isolated, NGC 6503 exhibits structural features suggesting subtle gravitational influences despite its loneliness. It reminds researchers that even galaxies appearing isolated may still participate in delicate cosmic relationships invisible at first glance. Another remarkable phenomenon found among void galaxies is polar ring formation. In these rare systems, a ring of gas, dust, and stars orbits perpendicular to the main galaxy disk, creating a structure that looks almost impossible. Astronomers believe these rings form through unusual gravitational captures or ancient interactions. Because void galaxies experience fewer disturbances, some of these delicate structures survive far longer than they might elsewhere in the universe. The cosmos preserves strange beauty in quiet places. Perhaps even more surprising are giant isolated spiral galaxies. Traditional models predicted that massive spiral galaxies would mainly form inside denser filaments of the cosmic web, where large amounts of matter could accumulate efficiently. Yet astronomers have discovered several surprisingly large spirals deep within underdense regions. These galaxies possess orderly rotating disks, active star formation, and enormous hydrogen clouds despite existing far from major cosmic structures. How they gathered enough matter remains an active area of research. Some scientists now believe cold gas streams may slowly feed isolated galaxies across billions of years. These invisible rivers of hydrogen could drift through faint dark matter filaments, threading even the emptiest voids. Although difficult to detect directly, simulations suggest such hidden structures may quietly shape galaxy growth across the universe. This idea transformed scientific understanding of voids. They're not truly disconnected emptiness. Instead, they may contain subtle, invisible scaffolding guiding matter through the darkness. Another astonishing discovery involves ultra-diffuse galaxies. These strange galaxies contain very few stars spread across enormous distances, making them appear like faint cosmic shadows. Some are nearly as large as the Milky Way, while containing only a tiny fraction of its stars. Their existence puzzled astronomers because such delicate systems should theoretically be vulnerable to gravitational disruption. Yet inside voids, where interactions are rare, ultra-diffuse galaxies may survive much longer. Voids act almost like protective shelters for fragile galactic structures. One especially interesting fact is that some void galaxies rotate more smoothly than galaxies in crowded environments. Because they experience fewer mergers and tidal interactions, their rotational dynamics remain relatively undisturbed. This makes them valuable laboratories for studying the relationship between visible matter and dark matter. In certain cases, astronomers found rotational speeds that seemed difficult to explain using ordinary models alone. These observations contribute to ongoing debates about whether dark matter fully explains galactic motion or whether gravity itself behaves differently on enormous scales. The loneliest galaxies may help reveal the deepest laws of physics. Astronomers have also noticed that black hole activity appears somewhat different inside certain void galaxies. Supermassive black holes normally grow through accretion, the process of gathering surrounding gas and matter. In dense environments, galactic interactions funnel large amounts of material toward galactic centers, feeding black holes and triggering energetic quasars or active galactic nuclei. But in void galaxies, these feeding events may occur less frequently. As a result, many void galaxies host quieter central black holes with lower activity levels. Yet surprisingly, some isolated galaxies still manage to produce active galactic nuclei despite their sparse surroundings. This suggests even isolated systems can transport matter toward their centers through internal processes alone. The universe, once again, proves more creative than expected. One deeply intriguing idea emerging from void studies is that isolation itself may influence galactic evolution almost as strongly as collisions do. In crowded regions, galaxies evolve through interaction. In voids, they evolve through patience, slow accretion, and long-term stability. Two entirely different evolutionary paths unfolding within the same universe. There is also evidence that void galaxies contain fewer satellite galaxies surrounding them. The Milky Way possesses dozens of small companion galaxies orbiting nearby, but isolated void galaxies often appear more solitary. This supports simulations suggesting that low-density environments naturally produce fewer secondary structures. Still, exceptions continue appearing. Some void galaxies unexpectedly possess companions, tidal streams, or faint surrounding dwarfs. Each new discovery forces astronomers to refine their models further. The deeper humanity studies the cosmos, the more complicated it becomes. And perhaps that complexity is part of what makes void galaxies so mesmerizing. They exist in places once considered nearly impossible for meaningful cosmic structures to survive. They form stars in darkness where matter is scarce. They preserve ancient galactic forms long erased elsewhere. They quietly challenge scientific assumptions without dramatic explosions or violent collisions. They simply continue existing, drifting through immense, silent expanses while carrying billions of stars inside them. Galaxies that should not exist, and yet they do. The deeper astronomers explored cosmic voids, the more they encountered galaxies that seemed almost disconnected from the ordinary rules governing the universe. Some appeared too large, some too active, some too delicate to have survived, and others behaved in ways so unusual that they force scientists to reconsider long-standing assumptions about how galaxies evolve across cosmic time. One of the most extraordinary discoveries involved galaxies with unexpectedly thin spiral disks. Normally, spiral galaxies gradually become thicker and more chaotic as gravitational interactions disturb their stars over billions of years. Small encounters with neighboring galaxies subtly alter stellar orbits, slowly puffing up the galactic disk. But inside certain voids, astronomers found spiral galaxies with remarkably thin and orderly structures, as though cosmic turbulence had barely touched them since their formation. These galaxies are sometimes described as super-thin galaxies. One well-known example is IC 5249, a galaxy so slender when viewed edge on that it resembles a glowing needle floating through darkness. Its thinness suggests an unusually calm evolutionary history with very few major disturbances. In denser regions of space, maintaining such fragile geometry for billions of years would be extremely difficult. Inside voids, however, serenity becomes possible. Another fascinating fact about void galaxies is the strange pace of their evolution. In crowded galaxy clusters, cosmic change can occur violently and quickly. Galaxies merge, black holes flare brightly, starbursts ignite, and gravitational forces reshape structures repeatedly. But in low-density voids, evolution often unfolds slowly, almost peacefully, over unimaginable timescales. Some astronomers describe these galaxies as under-evolved. This does not mean primitive in a simplistic sense. Rather, many void galaxies appear to have experienced fewer transformative events compared to galaxies of similar size elsewhere. Their histories contain fewer mergers, fewer tidal disruptions, and fewer bursts of catastrophic activity. In a way, they're quieter biographies written across billions of years. One especially curious discovery involves galaxies with enormous amounts of unused gas. Astronomers expected isolated galaxies to gradually consume their gas supplies over time. Yet several void galaxies contain far more hydrogen than predicted. Some possess giant invisible reservoirs capable of fueling star formation for billions of additional years. This suggests that gas may continue flowing slowly into these galaxies from surrounding intergalactic space. The process is sometimes called cold accretion. Unlike dramatic galactic mergers, cold accretion is subtle and nearly invisible. Streams of relatively cool hydrogen gas drift along faint cosmic filaments, gradually feeding galaxies over immense timescales. Computer simulations suggest this mechanism may be especially important inside void environments where violent interactions are rare. If true, some void galaxies may survive through cosmic nourishment so gentle that no human civilization could ever directly witness it unfolding. There are also galaxies inside voids that appear surprisingly isolated even from dark matter structures. This is deeply puzzling because dark matter halos are believed to play a crucial role in galaxy formation. Ordinary matter falls into these halos, eventually forming stars and galaxies. Yet certain void galaxies seem to exist in environments with unusually weak surrounding structures. Researchers continue debating whether these observations reveal gaps in current cosmological models or simply limitations in available data. Either possibility is exciting. Another strange category involves galaxies with asymmetrical shapes despite apparent isolation. Normally, distorted structures suggest gravitational interactions with nearby neighbors. Yet astronomers occasionally find isolated void galaxies with warped disks, lopsided spiral arms, or displaced gas clouds, even when no obvious companion galaxies exist nearby. What caused these distortions? Some scientists suspect ancient encounters occurred billions of years ago before the galaxies drifted deeper into the void. Others suggest interactions with invisible dark matter substructures may subtly influence galactic geometry. There are even theories proposing that intergalactic gas flows themselves can create long-term asymmetries. The universe rarely leaves simple answers. One remarkable discovery came from surveys conducted by the Sloan Digital Sky Survey, which identified thousands of galaxies inhabiting low-density cosmic regions. These observations revealed patterns that surprised researchers. Void galaxies were not merely random leftovers scattered through space. Many displayed consistent differences in color, star formation activity, morphology, and gas content compared to galaxies living in dense clusters. Environment clearly mattered. Where a galaxy lives influences how it ages. This idea, known as environmental dependence, became increasingly important in modern cosmology. Galaxies are not isolated machines evolving independently. Their surroundings, whether crowded or empty, shape their destiny across billions of years. And nowhere is this contrast clearer than inside cosmic voids. Some void galaxies also appear unusually rich in dark matter relative to their visible stars. In certain dwarf galaxies, dark matter may dominate so strongly that ordinary matter becomes only a tiny fraction of the total mass. These systems provide important laboratories for testing dark matter theories because external gravitational influences remain relatively minimal. In fact, astronomers often study dwarf void galaxies specifically to investigate one of cosmology's biggest mysteries. While the number of observed dwarf galaxies differs from predictions made by certain simulations, computer models of dark matter distribution suggest the universe should contain far more small galaxies than astronomers currently observe. This discrepancy, sometimes called the missing satellites problem, remains unresolved. Void environments may help researchers understand whether faint dwarf galaxies are simply difficult to detect or whether existing theories require refinement. The emptiest places may contain hidden populations still waiting to be discovered. Another deeply intriguing phenomenon is the presence of isolated starburst galaxies inside voids. Starburst galaxies experience intense episodes of star formation, producing new stars at extraordinarily high rates. Such events are often associated with galactic collisions or mergers. Yet a handful of void galaxies somehow trigger starbursts despite existing far from obvious interaction partners. How can a lonely galaxy suddenly ignite with stellar activity? Some researchers believe internal instabilities within massive gas disks may trigger these events naturally. Others suspect tiny invisible companion galaxies may occasionally pass nearby without easy detection. Regardless of the mechanism, these isolated starbursts reveal that galaxies do not always require dramatic external triggers to transform themselves. Even in solitude, the cosmos remains active. Astronomers have also discovered faint chains of galaxies stretching across certain voids, like fragile bridges connecting distant regions of the cosmic web. These structures are incredibly sparse compared to dense filaments, yet they hint that voids may contain more hidden organization than previously imagined. The universe may never allow perfect emptiness. Everywhere scientists search, some degree of structure appears. One especially calming thought emerges when considering the future of void galaxies. As cosmic expansion accelerates due to dark energy, distant galaxies gradually move farther apart. Over trillions of years, many galaxies outside local gravitational groups may disappear beyond observable horizons entirely. The universe will become darker and lonelier. In a sense, cosmic voids may represent glimpses of the universe's distant future. Vast expanses of darkness, isolated islands of stars separated by unimaginable distances, quiet galaxies drifting alone through an ever-expanding cosmos. This future solitude gives void galaxies an almost melancholic beauty. They are not merely scientific curiosities. They are previews of cosmic destiny itself. And still, despite their isolation, these galaxies continue creating stars. Nebulas still collapse. Planetary systems still form. Ancient suns still rise over worlds no human being will ever see. Another surprising fact is that some void galaxies contain bars, elongated stellar structures crossing their centers, despite the apparent lack of interactions thought to help form them. Galactic bars influence gas movement and star formation within galaxies, and their presence inside isolated systems suggests internal gravitational dynamics alone can create surprisingly complex structures. The more astronomers learn, the clearer one truth becomes. The universe is capable of building extraordinary complexity even in near emptiness. Void galaxies are living proof of this. They challenge assumptions about how much matter is required for large-scale organization. They reveal that quiet environments can preserve delicate structures erased elsewhere. They demonstrate that isolation can shape cosmic evolution just as powerfully as collision and chaos. And perhaps most beautifully, they remind humanity that the cosmos does not reserve wonder only for its brightest places. Even the loneliest regions contain galaxies of breathtaking scale, hidden rivers of gas, silent rotating spirals, faint newborn stars, invisible dark matter halos, and mysteries still unresolved. Far from the crowded brilliance of galaxy clusters, these isolated systems drift through immense darkness with quiet persistence. Galaxies that, by all expectations, should have failed to form. Galaxies that should have faded long ago. Galaxies that should not exist. Yet they remain there still, glowing softly inside the silent oceans of the universe. Chapter 3. Inside the loneliest regions in the universe. There are places in the universe where distance becomes almost impossible for the human mind to truly understand. Not merely the distance between stars, not even the distance between galaxies, but distances so enormous that entire galaxy clusters vanish into isolation, leaving behind expanses of darkness stretching across hundreds of millions of light years with barely anything at all inside them. These are the deepest cosmic voids, the loneliest regions in the known universe. To imagine standing inside one of these voids is to imagine a night sky unlike anything humanity has ever seen. On Earth, even far from city lights, the heavens glow with countless stars belonging to the Milky Way galaxy. Through telescopes, astronomers can see thousands of distant galaxies scattered across every tiny patch of sky. The observable universe appears crowded with light. But deep inside a massive cosmic void, much of that brilliance would disappear. Nearby galaxies would become extraordinarily rare. Great cosmic structures would lie unimaginably far away. The universe itself might appear emptier, darker, and quieter than any civilization could naturally expect. One of the first major facts astronomers learned about cosmic voids is that they are not random gaps. They are fundamental parts of the large-scale structure of the cosmos. After the Big Bang, matter in the young universe was not distributed perfectly evenly. Tiny fluctuations in density existed everywhere. Some regions slightly denser, others slightly emptier. Over billions of years, gravity amplified these differences. Dense regions attracted more matter, eventually forming galaxies, clusters, and giant filaments. Meanwhile, underdense regions lost matter to their surroundings, gradually becoming larger and emptier. This process created the cosmic web, a colossal network where galaxies gather along interconnected filaments while vast voids expand between them like bubbles growing inside rising foam. The scale of this structure is staggering. Some voids measure more than 100 million light-years across. Others, known as supervoids, stretch even farther. These are among the largest known structures in existence. Though structure may sound strange when describing regions defined mostly by absence, yet absence itself shapes the universe profoundly. One famous example is the Boötes void. Discovered in 1981 by astronomer Robert Kirshner and his team, the Boötes void shocked scientists because of its immense size. It spans roughly 330 million light-years across and contains far fewer galaxies than expected for a region of that volume. At first, researchers jokingly called it the Great Nothing. The nickname captured the emotional impact of the discovery. Humanity had uncovered a region so empty that it seemed almost unnatural. Yet over time, astronomers found that even the Boötes void contains galaxies, just very few of them compared to denser cosmic environments. If the Milky Way sat inside the center of such a void, neighboring major galaxies might lie tens of millions of light years away. Civilizations there could grow up beneath much darker skies. Some cosmologists have even wondered whether intelligent beings evolving inside deep voids might struggle to discover the expansion of the universe or the true nature of cosmic structure, because so few galaxies would be visible nearby. Their astronomy would be fundamentally different. Another fascinating fact is that voids are not static. They evolve continuously. As the universe expands, matter flows outward from underdense regions toward denser structures. This causes voids to grow larger over time. Simulations show that smaller voids can merge together, forming giant supervoids through a process somewhat similar to soap bubbles joining into larger bubbles. In a sense, emptiness expands. The universe slowly organizes itself into sharper contrasts between crowded regions and lonely ones. Astronomers studying void expansion discovered something remarkable. Galaxies near the edges of voids tend to move away from the centers. Gravity from surrounding filaments and clusters pulls matter outward, effectively evacuating the void further over billions of years. This creates subtle but measurable motions across enormous cosmic distances. One especially interesting region is the local void, located relatively close to humanity's own galactic neighborhood. The local void borders the local group, which contains the Milky Way, the Andromeda Galaxy, and dozens of smaller galaxies. For years, astronomers struggled to map this region because dust and stars from the Milky Way obscured observations. But modern surveys revealed that the local void is indeed extremely underdense. Even more intriguingly, evidence suggests the Milky Way itself may be partially influenced by the gravitational effects surrounding this emptiness. Our galaxy is not isolated from the void. It exists beside it, drifting within the broader architecture of the cosmic web. Another astonishing fact is that cosmic voids contain extremely low matter densities, often only about 10% of the average cosmic density, sometimes even less. Yet, empty does not mean completely vacant. Voids still contain dark matter. They still contain faint hydrogen gas. They still contain radiation left over from the Big Bang. And occasionally, they contain lonely galaxies quietly drifting through darkness. The amount of ordinary matter inside these regions is simply far lower than average. One particularly mysterious feature of voids involves temperature. In galaxy clusters, enormous clouds of gas become heated to millions of degrees through collisions and gravitational compression. These hot gases emit strong X-rays detectable across the universe. But inside voids, the lack of interactions means temperatures remain far colder and calmer overall. These are among the least energetic large-scale environments known to science. And yet, even there, the universe remains active. Tiny galaxies continue forming stars. Invisible gas flows drift across intergalactic distances. Dark matter shapes gravitational fields silently. Nothing in the cosmos ever becomes truly still. Astronomers have also discovered that galaxies inside voids tend to differ systematically from galaxies elsewhere. Many are smaller, bluer, and richer in hydrogen gas. Their isolation allows them to evolve more gently, without frequent collisions disrupting their structures. Some researchers compare void galaxies to wildlife living on isolated islands. Separated from larger ecosystems, they evolve along unique paths. Another curious observation involved galaxy spin alignment. Studies suggest that galaxies near void edges may rotate in preferred orientations relative to the surrounding cosmic web. The geometry of enormous large-scale structures appears to influence how galaxies acquire angular momentum during formation. The shape of emptiness affects the spinning of galaxies. This is one of the strangest truths in cosmology. Even regions defined by absence can exert subtle influence across the universe. There is also evidence that voids may help scientists test theories of gravity itself. Certain alternative models predicting modifications to Einstein's general relativity produce different effects inside low-density environments than standard cosmological models. Because voids contain less matter and weaker gravitational complexity, they become ideal testing grounds for studying how gravity behaves across gigantic scales. The emptiest places may reveal whether humanity fully understands space-time. One remarkable discovery came from observations of faint dwarf galaxies hidden inside voids. These tiny galaxies are difficult to detect because they contain relatively few stars. Yet surveys increasingly reveal that voids may host larger populations of faint dwarfs than previously realized. Some may remain undiscovered even now. Future observatories like the Vera C. Rubin Observatory are expected to uncover vast new catalogs of dim galaxies across low-density regions. Astronomers anticipate these observations could dramatically improve understanding of dark matter distribution and galaxy evolution. Perhaps the most emotionally powerful aspect of cosmic voids is their scale. Human beings evolved on a small rocky world orbiting an ordinary star in one spiral arm of a galaxy among trillions. Yet even within this incomprehensibly large universe, there exist regions so empty that they redefine human understanding of loneliness itself. And still, within those silent expanses, galaxies survive. Stars continue shining. Planets may orbit unseen suns. Life, perhaps somewhere, could quietly emerge beneath skies darker than anything humanity has ever known. The universe does not fear emptiness. It shapes entire cosmic landscapes from it. The deeper scientists look into cosmic voids, the more these silent regions begin to feel less like empty gaps and more like hidden worlds with their own strange rules. At first glance, voids appear simple. Fewer galaxies, less matter, more darkness. But modern astronomy has revealed that these lonely regions are extraordinarily important to understanding the universe itself. In many ways, voids behave like giant natural laboratories where the normal noise of crowded cosmic environments fades away, allowing subtle physical processes to become easier to observe. One fascinating fact is that light behaves differently while crossing immense voids. When photons travel through regions of varying gravity, their energy changes slightly. This effect becomes especially noticeable across gigantic cosmic distances. In expanding voids, photons entering and leaving the region experience tiny shifts in energy because the gravitational environment changes while the light travels through it. This phenomenon contributes to something called the integrated Sachs-Wolf effect. Though the name sounds complex, the idea is elegant. Ancient light from the Big Bang passes through evolving cosmic structures, including voids and galaxy clusters. As it does, the changing gravitational landscape slightly alters the light's temperature and energy. By studying these subtle distortions in the cosmic microwave background, astronomers can gather clues about dark energy, the mysterious force accelerating the expansion of the universe. Incredibly, even emptiness leaves fingerprints on ancient light. Another extraordinary fact is that voids may influence galaxy motion across hundreds of millions of light years. Gravity is often imagined only as a pulling force from massive objects. But in cosmology, underdense regions also shape movement because matter naturally flows away from emptiness toward denser regions. Galaxies near large voids experience these enormous gravitational imbalances over billions of years. Some astronomers believe giant voids contribute significantly to large-scale cosmic flows, the slow drifting motions of galaxies through space. Even the absence of matter can redirect the architecture of the universe. One particularly mysterious region is the KBC void, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie. According to some studies, the Milky Way may reside within a relatively underdense region hundreds of millions of light-years wide. If true, this could influence certain measurements of cosmic expansion. The idea remains debated among cosmologists, but it highlights how local void environments may subtly affect humanity's observations of the universe itself. Perhaps even more intriguing is the emotional perspective this creates. Humanity may already live near a cosmic emptiness without realizing how unusual our location truly is. Astronomers have also discovered that voids can affect galaxy evolution through isolation alone. In crowded galaxy clusters, galaxies constantly encounter one another. These interactions trigger starbursts, distort structures, and feed central black holes. But inside voids, galaxies often evolve with far less interference. This creates remarkably calm cosmic histories. Some void galaxies may go billions of years without major mergers. Their stars orbit quietly. Their spiral arms remain intact. Their gas disks survive largely undisturbed. These galaxies preserve ancient dynamical conditions that vanished elsewhere long ago. They are cosmic survivors of serenity. Another surprising fact is that voids may contain magnetic fields. Although extremely weak, intergalactic magnetic fields appear to thread through parts of the cosmic web, including low-density regions. Scientists still do not fully understand how these enormous magnetic structures formed. Some theories suggest they originated shortly after the Big Bang itself, while others propose they developed gradually through astrophysical processes over billions of years. Studying magnetic fields inside voids could help reveal the early history of the universe. Because voids experience fewer energetic disturbances, ancient magnetic signatures may survive there more clearly than in crowded regions. There is also growing evidence that tiny amounts of warm-hot intergalactic gas drift through void boundaries and filaments. This material is incredibly difficult to detect because it emits very little light. Yet astronomers believe much of the universe's missing ordinary matter may actually exist within these faint diffuse gas structures. In other words, part of the universe may be hiding inside, near invisibility. One especially curious phenomenon involves void walls. Although void centers remain sparsely populated, their edges often contain thin sheets and filaments of galaxies, surrounding the emptiness like coastlines around giant cosmic oceans. These boundaries become regions where matter accumulates as voids expand. The contrast can be dramatic. A galaxy drifting near the center of a void may have few neighbors within tens of millions of light years, while galaxies near the boundary suddenly encounter denser cosmic environments. This sharp transition influences galactic behavior significantly. Another remarkable fact is that some simulations predict voids may eventually dominate the visible structure of the universe. As dark energy continues accelerating cosmic expansion, galaxies outside local gravitational groups will move farther apart over trillions of years. the observable universe will become increasingly fragmented into isolated regions separated by expanding darkness. Future cosmic civilizations may witness skies far emptier than ours. Many distant galaxies currently visible from Earth will eventually disappear beyond observable horizons entirely. The night sky itself will slowly lose its deep extragalactic richness. In a profound sense, cosmic voids provide glimpses into that distant future. Astronomers also study voids to test whether the universe appears statistically uniform on the largest scales. According to the cosmological principle, the universe should look roughly similar overall regardless of location when viewed across enormous distances. Mapping void distributions helps scientists examine whether this assumption remains accurate. So far, observations generally support large-scale uniformity, though certain anomalies continue inspiring debate. The emptiest regions still challenge cosmology. One particularly fascinating discovery involves tiny dwarf galaxies hidden inside deep voids. These galaxies often contain very low metallicities, meaning their stars form from relatively chemically primitive gas. Because heavy elements accumulate through generations of stellar evolution, low metallicity galaxies may resemble conditions common in the early universe. Studying them allows astronomers to investigate how the first galaxies may have behaved shortly after cosmic dawn. In a way, voids preserve ancient memories. Some astronomers have even proposed that isolated void environments could influence the probability of advanced civilizations emerging. In crowded regions, frequent supernovae, black hole activity, and galactic collisions may create more hazardous cosmic conditions. Void galaxies, by contrast, experience fewer large-scale disturbances. Could isolated galaxies provide calmer environments for life to develop over immense timescales? No one knows, but the question itself reveals how cosmic structure shapes even humanity's imagination. Another extraordinary fact concerns the sheer rarity of interactions inside the deepest voids. In dense galaxy clusters, mergers happen relatively often across cosmic timescales. But certain void galaxies may spend their entire existence without experiencing a major collision. Imagine an entire galaxy evolving peacefully for billions upon billions of years. No catastrophic mergers, no tidal destruction, just quiet rotation beneath dark skies. This peacefulness gives void galaxies a haunting beauty unlike anything else in astronomy. The more humanity studies these regions, the clearer it becomes that emptiness is not absence in a simple sense. Voids possess structure, motion, evolution, magnetic fields, hidden gas, dark matter, expanding boundaries, and subtle gravitational effects shaping the cosmos itself. They are living components of the universe. And perhaps most astonishing of all, these immense lonely expanses occupy most of cosmic volume. Galaxy clusters and filaments contain much of the universe's visible matter, but voids dominate its space. Most of the universe is emptiness. Yet even that emptiness participates in the grand design of cosmic evolution. Far beyond crowded galaxies and brilliant quasars, deep within silent oceans stretching across unimaginable darkness, lonely galaxies continue drifting through the void. Their stars still shine, their planets still orbit, and through their quiet existence, they continue revealing secrets about gravity, dark matter, dark energy, cosmic history, and the ultimate destiny of the universe itself. Chapter 4. The Strange Physics of Cosmic Void. At first glance, cosmic voids appear simple. Less matter, less light, less activity. But beneath that apparent simplicity lies some of the strangest physics in the known universe. For astronomers and cosmologists, voids are not merely empty regions between galaxies. They are enormous laboratories where the hidden rules of the cosmos become easier to observe. In crowded regions of space, gravity, radiation, galactic collisions, magnetic turbulence, and black hole activity create layers of complexity that can obscure subtle physical effects. Inside voids, much of that cosmic noise fades away, and in the silence, deeper mysteries emerge. One of the most fascinating facts about cosmic voids is that they expand faster than denser regions around them. This sounds almost impossible at first. The universe as a whole is expanding everywhere. So how can one region expand faster than another? The answer lies in gravity. Dense regions filled with galaxies exert strong gravitational attraction, slowing local expansion slightly because matter pulls inward. Voids, however, contain much less matter. With weaker gravitational resistance, space inside these regions stretches more rapidly over time. In a sense, emptiness accelerates. This creates a remarkable effect where voids grow larger and emptier as billions of years pass. Matter gradually flows away from underdense regions toward surrounding filaments and galaxy clusters. The cosmic web sharpens itself through this process, increasing the contrast between crowded and lonely regions of the universe. Astronomers sometimes describe voids as the breathing spaces of the cosmos. Another extraordinary fact involves time itself. According to Einstein's theory of general relativity, gravity affects the flow of time. Clocks inside stronger gravitational fields run slightly slower than clocks in weaker fields. Since voids contain less matter and therefore weaker gravity overall, time technically passes a tiny bit faster inside them compared to denser regions. The difference is extremely small, far beyond ordinary human perception. Yet across enormous cosmic distances and billions of years, even tiny relativistic effects become scientifically meaningful. The emptiest places in the universe experience time differently. One especially important reason scientists study voids is because they provide cleaner environments for testing cosmological theories. In crowded galaxy clusters, complex gravitational interactions make observations difficult to interpret. But inside voids, the relative simplicity allows researchers to isolate subtle effects more clearly. This is particularly useful when studying dark energy. Dark energy remains one of the greatest mysteries in modern science. Observations show that the universe's expansion is accelerating, yet nobody fully understands why. Whatever dark energy is, it appears to dominate the large-scale behavior of the cosmos. And cosmic voids are highly sensitive to its influence. Because voids expand faster and evolve differently than dense regions, their growth patterns provide important clues about cosmic expansion history. By carefully measuring the sizes, shapes, and distribution of voids across the universe, astronomers can test whether current models of dark energy accurately describe reality. The universe hides clues about its destiny inside its emptiest regions. Another strange phenomenon connected to voids involves gravitational lensing. Normally, gravity bends light traveling through space. Massive galaxy clusters can distort and magnify distant galaxies behind them like gigantic cosmic lenses. But voids produce the opposite effect. Instead of concentrating light, they slightly disperse it. As light crosses an underdense region, the weaker gravitational field causes subtle distortions detectable by sensitive instruments. This is known as weak gravitational lensing by voids. Although the effect is extremely faint, Astronomers can measure it statistically across large surveys. Even emptiness bends light. One fascinating aspect of void physics is the behavior of dark matter within these regions. Dark matter cannot be seen directly because it does not emit or absorb light. Yet its gravitational influence shapes galaxies and the cosmic web itself. Simulations suggest that voids are not completely devoid of dark matter. Instead, they contain thin, diffuse distributions stretching across enormous distances. Some researchers describe these structures as ghostly scaffolding hidden inside cosmic darkness. Tiny dark matter filaments may quietly connect isolated galaxies deep within voids, allowing matter to flow slowly over billions of years. Detecting these structures directly remains extremely difficult, but computer models strongly suggest their existence. Another remarkable fact is that cosmic voids help scientists test alternative theories of gravity. Einstein's general relativity has passed countless experimental tests, yet certain cosmological puzzles remain unresolved. Some physicists propose modified gravity theories that behave differently on extremely large scales. Interestingly, these alternative models often predict noticeable differences specifically inside low-density environments like voids. In denser regions, ordinary gravity dominates strongly enough that alternative effects may become hidden. But in voids where gravity is weaker, subtle deviations could emerge more clearly. This makes cosmic voids among the most valuable testing grounds in modern cosmology. One especially mysterious observation involves the shapes of voids themselves. Voids are not perfect spheres. They stretch, merge, deform, and evolve in complex ways depending on surrounding matter distributions. Some resemble elongated tunnels, while others appear more bubble-like or irregular. Their geometry reflects the hidden architecture of the cosmic web. Astronomers use sophisticated algorithms to identify and map these structures across galaxy surveys. Surprisingly, defining where a void truly begins or ends can be challenging because density changes gradually rather than abruptly. The universe does not draw sharp borders around emptiness. Another curious fact concerns temperature fluctuations in the cosmic microwave background. The cosmic microwave background is ancient radiation left over from the Big Bang, filling all of space almost uniformly. Yet tiny temperature variations exist across it. Some of these fluctuations appear connected to massive cosmic structures, including voids. One famous example is the cold spot, an unusually cool region in the microwave background discovered through satellite observations. Some researchers propose that a gigantic supervoid located between Earth and the cold spot could partially explain the anomaly by affecting photons traveling through it. Though debates continue, the idea demonstrates how enormous voids may influence light that has crossed billions of years of cosmic history. Another extraordinary feature of voids is their low collision rate. In galaxy clusters, galaxies frequently interact gravitationally. Gas clouds collide, stars experience tidal disruptions, and supermassive black holes feed actively. Inside deep voids, however, galaxies may drift for billions of years without close encounters. This creates unusually stable physical environments. Spiral arms survive longer. Gas disks remain intact. Delicate structures avoid destruction. The physics of isolation becomes a defining force. Some astronomers believe this calmness allows void galaxies to preserve conditions resembling earlier epochs of the universe. Studying them may therefore provide indirect glimpses into ancient cosmic history. Another fascinating phenomenon is known as void alignment. Research suggests that galaxies near void boundaries may orient themselves relative to surrounding large-scale structures. The shapes and spins of galaxies appear influenced by the geometry of nearby emptiness itself. This means the universe's largest structures subtly guide the motions of individual galaxies. The idea feels almost philosophical. Gigantic regions of darkness shaping the dance of stars. Astronomers also study sound like phenomena connected to the early universe called baryon acoustic oscillations. Shortly after the Big Bang, pressure waves moved through hot plasma, filling the young cosmos. These ancient ripples left faint imprints on galaxy distributions observable today. Voids help scientists measure these patterns with greater precision. By mapping void locations alongside galaxy clusters, researchers refine estimates of cosmic expansion rates and large-scale geometry. Even silence contains echoes of the Big Bang. Perhaps the strangest truth about cosmic voids is that they dominate the universe by volume. Galaxies, stars, nebulae, and clusters may seem visually important, but most of cosmic space consists of immense underdense regions. The visible brilliance of the universe is concentrated along thin filaments surrounding enormous darkness. Humanity exists inside one small luminous thread woven through a cosmos mostly composed of vast quiet emptiness. And yet that emptiness is not passive. It expands. It bends light. It influences gravity. It shapes galaxies. It preserves ancient structures. It carries hidden dark matter and faint magnetic fields across unimaginable distances. The more scientists study voids, the more they realize these silent regions are not empty gaps in the universe. They're active participants in cosmic evolution itself. If humanity could somehow drift silently through the center of a giant cosmic void, the experience would feel unlike anything imaginable. There would be no nearby galaxies blazing across the sky, no crowded clusters glowing in the distance. Only scattered islands of faint starlight, separated by oceans of darkness so vast that the human mind would struggle to comprehend them. And yet beneath that silence, physics would still be unfolding everywhere. Invisible forces would continue shaping the universe with quiet precision. One of the strangest aspects of void physics is how these regions influence the motion of galaxies far beyond their boundaries. Astronomers once imagined cosmic expansion as relatively smooth on large scales, but observations revealed something more dynamic. Galaxies drift through space with additional motions called peculiar velocities, movements caused by gravitational attraction from surrounding matter distributions. Large voids contribute strongly to these flows. As matter evacuates underdense regions over billions of years, galaxies near void edges gradually migrate outward toward denser cosmic filaments and clusters. This creates enormous patterns of motion spanning hundreds of millions of light years. The universe behaves almost like a vast gravitational weather system. Another extraordinary fact is that voids may help scientists understand whether dark energy changes over time. Most current cosmological models assume dark energy behaves as a constant property of space itself. But some alternative theories suggest its strength may evolve gradually across cosmic history. Because void expansion is highly sensitive to the rate of cosmic acceleration, studying void growth across different eras allows astronomers to test these possibilities. In other words, the emptiest regions of space may reveal whether the universe's acceleration is truly constant or part of a deeper, evolving process. This is one reason modern galaxy surveys devote enormous effort to mapping cosmic voids accurately. Projects involving observatories like the Dark Energy Survey and the European Space Agency continue collecting data from millions of galaxies to refine these measurements. Every newly mapped void becomes another clue about the structure and fate of the cosmos. Another fascinating physical effect inside voids involves entropy. Entropy is often described as the tendency of systems toward increasing disorder. In cosmology, the large-scale evolution of the universe gradually produces more separation, more expansion, and more thermodynamic isolation over time. Voids embody this process beautifully. As the universe ages, matter flows into denser structures, while voids become larger and emptier. The cosmos slowly organizes itself into isolated islands surrounded by expanding darkness. In a profound sense, cosmic voids represent the long-term thermodynamic direction of the universe itself. They are previews of the far future. Another curious fact is that some voids contain tiny galaxy chains stretching across their interiors. These faint structures are much less dense than ordinary cosmic filaments, yet they suggest matter rarely disappears completely from any region. Even the loneliest expanses preserve traces of hidden organization. Astronomers sometimes refer to these faint structures as mini-filaments or tenuous bridges. They may guide gas flows toward isolated galaxies, helping sustain slow star formation over billions of years. The universe seems reluctant to allow perfect emptiness anywhere. One particularly mysterious phenomenon involves the polarization of light crossing large-scale structures. Light waves can become subtly aligned or distorted while traveling through magnetic fields and gravitational environments. Researchers studying distant radio signals have found hints that large-scale cosmic structures, including void boundaries, may influence polarization patterns in ways not yet fully understood. Some findings remain controversial, but they raise profound questions about whether hidden cosmic-scale magnetic fields or unknown physical effects shape light propagation across the universe. The deeper scientists investigate voids, the stranger the physics becomes. Another remarkable discovery is that certain void galaxies contain unexpectedly ordered rotation despite their isolation. Normally, galaxy formation involves chaotic interactions and turbulent gas flows. Yet some isolated galaxies display remarkably stable rotational behavior, extending far beyond visible stellar disks. These systems help astronomers study the relationship between dark matter and ordinary matter more clearly. In many galaxies, outer stars orbit so quickly that visible matter alone cannot explain their motion. Dark matter halos provide the missing gravitational influence. Void galaxies, with fewer external disturbances, offer cleaner environments for measuring these effects. Some observations have even fueled debates about whether gravity itself behaves differently on extremely large scales. Alternative theories like modified Newtonian dynamics attempt to explain galactic rotation without dark matter, though most cosmologists still favor dark matter models overall. Voids remain important testing grounds because their simplified environments reduce observational complications. The quietest places may reveal the deepest physical truths. Another fascinating aspect of voids involves cosmic rays. Cosmic rays are high-energy particles traveling through space at enormous speeds. In dense galaxy clusters, magnetic turbulence and energetic black hole activity strongly influence cosmic ray behavior. But inside voids, magnetic fields appear weaker and matter far sparser. This changes how energetic particles propagate across intergalactic distances. Some ultra-high-energy cosmic rays may travel through voids with relatively fewer interactions, potentially carrying information about distant astrophysical sources across billions of light years. Even the emptiest regions become pathways for invisible particles racing through the universe. Astronomers have also explored whether voids affect the formation of supermassive black holes. Most galaxies contain giant black holes at their centers, including the Milky Way's Sagittarius A. In crowded environments, galaxy mergers help funnel gas inward, feeding these black holes and triggering active galactic nuclei or quasars. But isolated void galaxies experience far fewer mergers. Yet surprisingly, some still host active central black holes. This suggests black hole growth can occur through slow internal processes alone, without requiring dramatic collisions. Even in cosmic solitude, galaxies continue evolving from within. Another extraordinary fact concerns quantum fluctuations in the early universe. Modern cosmology proposes that tiny quantum variations shortly after the Big Bang eventually grew into the large-scale cosmic structures seen today. Regions slightly denser accumulated matter, while slightly emptier regions became voids. This means today's giant cosmic voids may ultimately trace their origins back to microscopic quantum fluctuations occurring billions of years ago. The largest empty regions in existence began as tiny uncertainties in the infant universe. It is one of the most astonishing connections in science, linking quantum physics to structures hundreds of millions of light years across. There's also evidence that voids may help constrain neutrino physics. Neutrinos are tiny, nearly massless particles flooding the universe in enormous numbers. Though difficult to detect, they influence cosmic structure formation subtly because their high velocities smooth matter distributions across large scales. The shapes and growth rates of voids depend partly on these effects. By comparing observed void structures to simulations, cosmologists can estimate limits on neutrino masses, one of the major unanswered questions in particle physics. Again, emptiness becomes a tool for understanding reality itself. Perhaps the most haunting physical truth about voids is how closely they resemble the universe's eventual future. Over unimaginable timescales, cosmic expansion driven by dark energy will isolate galaxies increasingly from one another. Distant structures will vanish beyond observable horizons. The universe will become darker, quieter, lonelier. Future observers may inhabit isolated galaxies surrounded by immense darkness, much like today's deepest voids. Most evidence of the Big Bang and large-scale cosmic web may eventually disappear from view entirely. In this sense, cosmic voids are not only remnants of structure formation. They are glimpses ahead in time. And yet, even there, physics continues unfolding. Gravity still shapes motion. Dark matter still weaves invisible scaffolding. Ancient radiation still crosses space. Stars still form. Galaxies still rotate. The universe remains alive even in its quietest places. Far beyond crowded clusters and brilliant nebulae, inside the silent expanses between the galaxies, the strange physics of cosmic voids continues shaping the destiny of everything. Chapter 5: Ancient Light from Empty Space. Long before galaxies existed, before stars ignited, before planets formed, before the universe contained anything resembling the cosmic structures humanity sees today, there was light, ancient light, a faint glow born in the aftermath of the Big Bang itself, still traveling silently through space nearly 13.8 billion years later. This radiation, known as the cosmic microwave background, fills every region of the universe. It drifts through galaxies, across intergalactic darkness, through clusters of matter, and even through the deepest cosmic voids. And surprisingly, those vast, empty regions help scientists understand this ancient light in extraordinary ways. One of the most remarkable facts about cosmic voids is that they interact with the oldest observable radiation in existence. Although voids contain relatively little matter, their immense size allows them to subtly alter photons crossing through them across billions of years. The effect is tiny, but on cosmic scales, tiny effects become measurable. The cosmic microwave background, often shortened to the CMB, formed roughly 380,000 years after the Big Bang. Before that time, the universe was so hot and dense that light could not travel freely. Space was filled with an opaque plasma of charged particles scattering photons constantly. Then the cosmos cooled. Electrons combined with nuclei to form neutral atoms, allowing light to finally move unhindered through space. The universe became transparent for the first time. The photons released during that ancient moment still exist today. They have stretched into microwave wavelengths due to cosmic expansion, becoming an almost perfectly uniform background glow surrounding the universe. Yet almost perfectly is important. Tiny temperature variations exist within the CMB, minute differences measuring only fractions of a degree. These fluctuations contain enormous scientific importance because they preserve information about the early universe and the growth of cosmic structure. And cosmic voids influence those ancient photons during their long journey across space. One especially fascinating phenomenon is called the integrated Sachs-Wolf effect. As photons travel through large cosmic structures, gravity affects their energy. When light enters a gravitational well, such as a galaxy cluster, it gains energy falling inward and loses energy climbing back out. If the gravitational environment remains perfectly stable, the gains and losses cancel almost exactly. But the universe is expanding, and dark energy changes how structures evolve over time. In expanding cosmic voids, gravitational conditions shift while photons pass through them. This causes tiny net energy changes detectable in the cosmic microwave background. In simple terms, empty regions slightly alter ancient light from the Big Bang. The scale of these structures matters enormously. A small void produces minimal effects, but gigantic supervoids spanning hundreds of millions of light years can leave measurable imprints on the microwave background itself. This realization transformed how astronomers viewed emptiness. Voids were no longer passive gaps between galaxies. They became active cosmological tools. One particularly mysterious example involves the famous cold spot. Discovered through satellite observations of the cosmic microwave background, the cold spot is an unusually cool region of sky larger and colder than expected from ordinary fluctuations alone. Scientists proposed several explanations over the years, ranging from statistical coincidence to exotic early universe physics. One hypothesis suggested a giant supervoid located between Earth and the cold spot might partially explain the anomaly. The idea was elegant. Photons crossing an enormous underdense region would lose slightly more energy than expected because of the evolving gravitational environment. This could produce a cooler patch in the microwave background. Although the debate remains unresolved, observations did reveal a significant supervoid in roughly the same direction. Even if it cannot fully explain the cold spot, the discovery demonstrated how profoundly voids can influence ancient cosmic light. Another extraordinary fact is that cosmic voids help scientists study dark energy indirectly. Dark energy dominates the large-scale expansion of the universe, yet its true nature remains unknown. Because the integrated Sachs-Wolf effect depends on evolving cosmic expansion, measuring how voids alter microwave background photons provides clues about dark energy's behavior. Astronomers combine galaxy surveys with microwave background maps to study these effects statistically across thousands of voids. The results help refine cosmological models describing the universe's expansion history. The emptiest regions of space become instruments for measuring the fate of the cosmos. Another remarkable aspect of ancient light inside voids involves temperature uniformity. The cosmic microwave background appears astonishingly smooth across the sky despite regions being separated by enormous distances. This uniformity puzzled scientists for decades because distant regions should never have communicated with one another under ordinary expansion alone. The solution became inflation theory. According to modern cosmology, the universe underwent an incredibly rapid expansion shortly after the Big Bang, stretching tiny quantum fluctuations across immense cosmic scales. These fluctuations later evolved into galaxies, clusters, filaments, and voids. In a profound sense, today's giant cosmic voids began as microscopic quantum irregularities inside the infant universe. The largest empty regions in existence trace their origins back to subatomic fluctuations billions of years ago. This connection between quantum physics and cosmic structure remains one of the most beautiful ideas in modern science. Another fascinating fact is that photons crossing voids travel through some of the least obstructed regions in the universe. Dense galaxy clusters contain hot gas, magnetic fields, and energetic particles capable of interacting with radiation in various ways. Voids, by contrast, provide relatively clean pathways across enormous distances. Ancient light can drift through these silent expanses with minimal interference. In a way, voids preserve clarity. Astronomers also study how radio signals from distant galaxies behave while crossing void environments. Because voids contain fewer free electrons and weaker magnetic turbulence, signals may travel differently compared to crowded cosmic regions. These subtle effects help researchers map intergalactic matter distribution and magnetic field structures across the universe. Even near emptiness leaves measurable signatures on traveling light. Another curious discovery involves gravitational lensing by voids. Normally, massive galaxy clusters magnify distant galaxies behind them through gravitational bending of light. Voids produce the opposite effect. Their lower density slightly reduces gravitational focusing, creating faint distortions detectable through careful statistical analysis. This phenomenon is sometimes called anti-lensing. Again, emptiness behaves actively rather than passively. One especially calming thought emerges when considering the age of the light crossing cosmic voids. Some photons currently passing through these lonely regions began their journey long before Earth existed. They traveled across billions of years while galaxies formed, stars exploded, planets emerged, and life slowly evolved on one small world orbiting an ordinary star. Ancient light continues crossing silent darkness even now. Astronomers using observatories, such as the Planck Space Observatory and the Wilkinson Microwave Anisotropy Probe, mapped the microwave background with extraordinary precision, revealing subtle temperature patterns connected to large-scale cosmic structure. These missions transformed humanity's understanding of the universe. They showed that emptiness itself carries information. Another remarkable fact is that voids may eventually dominate observable cosmic structure as the universe ages. Dark energy causes accelerating expansion, gradually increasing the isolation between galaxies. Over trillions of years, distant galaxies will disappear beyond observable horizons. Future civilizations may inhabit skies resembling deep cosmic voids. Most of the visible universe will slowly fade away. And yet, ancient microwave radiation will continue crossing space for unimaginable spans of time. The oldest light in existence drifting endlessly through expanding darkness. Cosmic voids remind humanity that emptiness is never truly empty. Even the loneliest regions contain ancient photons carrying memories from the birth of the universe itself. Silent light crossing silent oceans of space. The universe remembers its beginning through light, not through written history, not through sound, but through ancient photons still drifting across space after nearly 13.8 billion years of travel. Every cosmic void, every lonely galaxy, every immense region of darkness remains filled with this faint afterglow from the birth of the cosmos. Even in the emptiest places imaginable, the universe is never completely dark. The ancient light is always there. One of the strangest facts about the cosmic microwave background is how weak it has become over time. When it first emerged shortly after the Big Bang, the universe glowed brilliantly with temperatures thousands of degrees hotter than today. But as space expanded, the wavelengths of those photons stretched slowly across billions of years. Now, the radiation measures only about 2.7 degrees above absolute zero. Yet despite its faintness, it remains one of the most important discoveries in scientific history. And cosmic void helps scientists read its hidden patterns more clearly. One especially fascinating phenomenon involves the Rees-Sayama effect, a subtle cousin of the integrated Sachs-Wolf effect. While the integrated Sachs-Wolf effect occurs because large-scale cosmic expansion changes gravitational environments over time, the Rees-Sayama effect emerges from evolving structures themselves. As massive voids expand and evolve, photons traveling through them experience tiny additional energy shift caused by changing gravitational geometry. The effect is incredibly faint. Detecting it requires enormous data sets and sophisticated statistical analysis. Yet studying these subtle distortions helps cosmologists understand how large-scale structures evolve under the influence of gravity and dark energy. Even ancient light notices the growth of emptiness. Another remarkable fact is that voids help astronomers separate different cosmological signals from one another. Observing the universe is difficult because many overlapping effects influence light simultaneously. Galaxy clusters, magnetic fields, hot gases, gravitational lensing, and cosmic expansion all leave signatures on photons crossing space. Void regions provide cleaner environments. Because they contain less matter and fewer energetic disturbances, scientists can isolate delicate effects more effectively there than in crowded cosmic regions. This makes voids essential for precision cosmology, the effort to measure the universe's properties with extraordinary accuracy. The quietest places often produce the clearest observations. Astronomers have also discovered that voids may influence polarization patterns in ancient radiation. Light waves possess orientations called polarization states, and certain cosmic processes subtly affect them. Mapping polarization across the microwave background helps researchers investigate conditions in the early universe, including possible traces of primordial gravitational waves. Although void-related polarization effects remain extremely subtle, they contribute to broader efforts aimed at understanding the universe's first moments after the Big Bang. The emptiest regions may preserve whispers from cosmic infancy, One particularly mysterious topic connected to voids involves anomalies in the cosmic microwave background itself. Most temperature fluctuations in the microwave background fit predictions from standard cosmological models remarkably well. Yet a few large-scale anomalies continue puzzling researchers. Certain regions appear slightly colder, aligned, or asymmetrical in unexpected ways. Some scientists suspect these features are simply statistical coincidences. Others wonder whether giant cosmic structures, including supervoids, contribute more strongly than previously realized. The debate remains unresolved, but it reveals how even nearly empty regions can become central to understanding the largest questions in cosmology. Another extraordinary fact is that voids help scientists measure baryon acoustic oscillations. Shortly after the Big Bang, the young universe behaved like a hot plasma where pressure waves moved through matter and radiation. These ancient sound waves left faint imprints on the distribution of galaxies and voids observable today. By measuring the characteristic scales of these patterns, astronomers use them as standard rulers for studying cosmic expansion. Voids contribute importantly to these measurements because their distribution reflects the same underlying primordial fluctuations that shaped galaxies and clusters. Even silence contains echoes of ancient cosmic sound. One fascinating aspect of ancient light-crossing voids is the enormous timescale involved. Some photons currently passing through a supervoid may have begun their journey before the Milky Way fully formed. They traveled while stars were born and died, while galaxies collided, while black holes grew, while planets cooled, and while life slowly emerged on Earth. The universe evolves continuously around traveling light. And yet those photons still carry information from the dawn of time. Another remarkable phenomenon involves the slight cooling of photons crossing expanding voids. As cosmic voids grow larger due to dark energy-driven expansion, photons passing through them can lose tiny amounts of energy. These changes are almost unimaginably small, yet modern instruments can detect statistical patterns across millions of observations. Humanity has built machines capable of measuring the influence of emptiness on ancient light across billions of light years. It is one of the greatest intellectual achievements in human history. Astronomers also use voids to test whether the laws of physics remain constant across the observable universe. If dark energy, gravity, or fundamental constants behave differently in low-density environments, void observations might reveal inconsistencies in cosmic microwave background measurements. So far, the universe appears remarkably consistent, but scientists continue searching carefully, because sometimes the smallest anomalies lead to the deepest revolutions in understanding. Another deeply calming thought emerges from these studies. Every cosmic void remains illuminated by the same primordial radiation. The oldest detectable light in the universe drifts equally through crowded galaxy clusters and lonely dark expanses alike. No region is completely isolated from cosmic history. Even the emptiest places remain connected to the Big Bang. One especially mysterious area of research involves whether giant voids could influence measurements of the Hubble constant, the rate at which the universe expands. Modern observations using different techniques produce slightly conflicting values for cosmic expansion, creating what scientists call the Hubble tension. Some researchers propose that local underdense regions might subtly affect certain measurements. While voids alone likely cannot fully resolve the discrepancy, they may contribute small corrections important for precision cosmology. Again, emptiness becomes scientifically significant. Another extraordinary fact concerns future observations. Upcoming observatories, such as the Nancy Grace Roman Space Telescope and the Square Kilometer Array, will map galaxies and cosmic structures with unprecedented detail. These projects are expected to identify enormous numbers of new voids across vast cosmic distances. Astronomers hope these surveys will improve measurements of dark energy, galaxy evolution, and ancient light interactions dramatically. The next generation of telescopes may reveal structures humanity has never imagined before. Perhaps even larger supervoids. Perhaps new anomalies in the microwave background. Perhaps entirely unexpected patterns hidden within cosmic emptiness. And through all these discoveries, one truth continues emerging again and again. The universe is shaped as much by emptiness as by matter. Voids are not meaningless gaps between galaxies. They influence light. They shape motion. They preserve ancient information. They magnify subtle physical effects impossible to study elsewhere. Most importantly, they remind humanity that the cosmos possesses depth even in silence. Far beyond the glowing galaxies visible in astronomy photographs lie immense dark oceans where ancient photons continue their endless journey. The oldest light in existence crosses those silent regions patiently, carrying memories from the beginning of time itself. And somewhere tonight, while Earth turns quietly beneath its atmosphere, ancient radiation from the Big Bang is passing through distant void galaxies, drifting across immense darkness older than stars, older than planets, older than life itself. Light from the birth of the universe, still traveling through empty space. Chapter 6. The Hidden Web Between the Galaxies, if the universe could be viewed from impossibly far away. Far beyond galaxies. Far beyond clusters. Far beyond the observable horizon itself. It would not appear as random points of light scattered through darkness. Instead, the cosmos would resemble an enormous web, a vast interconnected structure stretching across billions of light years, where galaxies gather along glowing filaments surrounding gigantic empty regions called voids. These filaments form the hidden architecture of the universe, an immense cosmic network connecting matter across unimaginable distances. Astronomers call it the cosmic web. And without it, galaxies like the Milky Way galaxy might never have formed at all. One of the most astonishing facts in modern cosmology is that galaxies are not distributed randomly throughout space. Instead, they cluster along gigantic filaments made of dark matter, gas, and galaxies woven together like threads through the universe. Between these threads lie the cosmic voids. The web and the voids depend on each other completely. Without emptiness, the web could not exist. And without the web, the voids would have no shape. This structure began forming shortly after the Big Bang. Tiny quantum fluctuations in the infant universe created slight density differences, some regions containing marginally more matter than others. Over billions of years, gravity amplified these differences. Dense regions attracted additional matter, eventually forming filaments and galaxy clusters. Meanwhile, underdense regions lost matter and expanded into enormous voids. The result was a universe resembling foam, sponge, or lace on scales almost too large for the human mind to comprehend. One especially fascinating fact is that dark matter plays the central role in building this web. Although invisible, dark matter exerts gravity. Scientists estimate it outweighs ordinary visible matter by roughly 5 to 1. Shortly after the Big Bang, dark matter began clumping together first, creating enormous gravitational scaffolding across the cosmos. Ordinary matter followed. Hydrogen gas flowed into dark matter filaments like rivers draining into valleys, eventually collapsing into stars and galaxies. In a profound sense, the visible universe formed along invisible structures. Another remarkable fact is that cosmic filaments can stretch hundreds of millions of light years across. These are among the largest known structures in existence. Galaxy superclusters connect through these enormous bridges while voids expand between them. One famous example is the Sloan Great Wall, a gigantic cosmic structure discovered through the Sloan Digital Sky Survey. It extends roughly 1.4 billion light-years across, containing countless galaxies arranged within interconnected filaments. Humanity exists inside one tiny section of this incomprehensibly vast network. Another extraordinary discovery is that galaxies appear to spin in relation to the cosmic web itself. Astronomers studying galaxy orientations found evidence that spiral galaxies often align their rotational axes relative to nearby filaments and void boundaries. Smaller galaxies tend to spin parallel to filaments, while larger galaxies sometimes rotate differently due to complex merger histories. The architecture of the universe influences how galaxies turn through space. It is almost as though galaxies inherit motion from the geometry surrounding them. Another fascinating fact is that much of the ordinary matter in the universe may exist hidden inside the web rather than within galaxies themselves. For decades, astronomers faced a mystery known as the missing baryon problem. Calculations predicted more ordinary matter should exist than observations could directly detect. Eventually, researchers realized much of this missing material likely resides in faint diffuse gas stretching through cosmic filaments. This material is called the warm, hot intergalactic medium. It is incredibly thin and difficult to observe because it emits very little light. Yet simulations suggest it forms enormous invisible rivers connecting galaxies across the cosmic web. Even the darkness between galaxies contains hidden oceans of matter. Astronomers have slowly begun detecting this elusive material using sensitive X-ray and ultraviolet observations. The discoveries confirm that filaments are not empty bridges, but active channels transporting gas and energy through the universe. Another remarkable aspect of the cosmic web involves galaxy feeding. Galaxies require fresh hydrogen gas to continue forming stars. In crowded regions, mergers provide some material, but along cosmic filaments, gas can also flow continuously toward galaxies through a process called cold accretion. These streams act like intergalactic supply lines. Even isolated void galaxies may receive gas through faint hidden filaments threading the darkness around them. This realization changed how astronomers understand galaxy evolution. Galaxies are not isolated islands passively drifting through space. They are connected to larger structures constantly influencing their growth. The universe behaves less like scattered objects and more like a living network. Another astonishing fact is that galaxy clusters form at intersections where multiple filaments meet. These nodes become some of the densest regions in the universe, containing thousands of galaxies bound together gravitationally. Between those crowded intersections stretch the giant empty voids. The contrast is extraordinary. Some regions contain enormous concentrations of matter and energy. Others remain vast, silent expanses with only a few lonely galaxies drifting through darkness. The cosmic web creates both extremes simultaneously. Astronomers using advanced computer simulations like the Millennium simulation recreated these structures virtually by modeling dark matter and cosmic expansion over billions of years. The resulting images closely resemble actual galaxy surveys, providing powerful evidence supporting modern cosmological theory. The simulations revealed something beautiful. Complex cosmic structure can emerge naturally from tiny fluctuations amplified by gravity over immense timescales. Another fascinating fact is that the cosmic web continues evolving even now. Void regions grow larger while filaments sharpen and galaxy clusters become more concentrated. Matter slowly drains away from underdense regions toward denser structures, increasing contrast across the universe. The cosmos is still organizing itself, and dark energy accelerates this process by driving cosmic expansion ever faster. Another curious phenomenon involves magnetic fields threading through cosmic filaments. Although extremely weak compared to those inside galaxies, intergalactic magnetic fields may stretch across enormous distances within the web. Scientists still debate exactly how these fields formed. Some theories suggest they originated shortly after the Big Bang itself. Others propose they developed gradually through astrophysical processes involving galaxies and black holes over billions of years. Studying these magnetic structures could reveal hidden chapters in cosmic history. One especially mysterious discovery came when astronomers observed quasars, extremely bright active galactic nuclei, whose light passed through cosmic filaments. The absorption signatures revealed faint gas structures connecting galaxies across intergalactic space. The universe contains far more hidden structure than visible light alone reveals. Another extraordinary fact is that the cosmic web influences temperature across the universe. Dense clusters contain hot X-ray emitting gas reaching millions of degrees due to gravitational compression and collisions. Voids remain far colder and calmer. Filaments occupy intermediate environments where diffuse gas slowly moves between structures. The universe possesses climates on cosmic scales, and everything connects through the hidden web. Perhaps the most emotionally powerful aspect of the cosmic web is what it reveals about humanity's place in existence. Earth is not isolated. The solar system belongs to the Milky Way. The Milky Way belongs to the local group. The local group lies along larger filaments connected to superclusters woven into the cosmic web itself. Humanity exists inside a vast interconnected structure spanning billions of light years. Invisible threads of gravity and dark matter bind the universe together, and between those threads drift the immense silent voids, oceans of darkness giving shape to the web surrounding them. The cosmic web is invisible to human eyes. No person standing beneath Earth's night sky can directly see the enormous filaments stretching across billions of light years. Even powerful telescopes reveal only fragments, galaxies glowing like scattered lanterns while the underlying structure remains mostly hidden. And yet everything in the observable universe is shaped by this unseen network. Galaxies form along it. Matter flows through it. Voids expand between its strands. Without the cosmic web, the universe would look entirely different. One of the most remarkable facts about the web is that its structure emerged naturally from tiny irregularities in the early universe. After the Big Bang, matter was distributed almost uniformly, but not perfectly. Minute density fluctuations existed everywhere. Differences so small they were measured in fractions of a percent. Over billions of years, gravity amplified those fluctuations into the gigantic structures seen today. This process transformed microscopic quantum variations into filaments spanning hundreds of millions of light years. The largest structures in existence grew from subatomic irregularities. Another fascinating fact is that dark matter determines the shape of the web long before visible galaxies appear. Computer simulations show dark matter collapsing into vast filamentary patterns early in cosmic history, forming enormous invisible highways through space. Ordinary matter then followed these gravitational pathways. Hydrogen gas collected inside the dark matter scaffolding, cooling and collapsing into stars and galaxies. In this way, dark matter became the hidden architect of the visible cosmos. Everything humanity sees in the night sky formed within an invisible framework. Another extraordinary discovery is that galaxies are not stationary within the web. They drift slowly along filaments over billions of years, pulled by gravity toward denser nodes and clusters. Entire galaxy groups migrate gradually through the cosmic network like leaves floating along slow-moving rivers. The Milky Way itself participates in these immense motions. Our galaxy moves relative to the cosmic microwave background at hundreds of kilometers per second, due partly to gravitational influences from surrounding structures, including giant clusters and nearby voids. Humanity is traveling through the web even now. One especially mysterious aspect of the cosmic web involves dark matter filaments crossing cosmic voids. Although voids contain far less matter than average, simulations suggest faint dark matter strands still pass through some regions of emptiness. These ghostly structures may connect isolated void galaxies and allow slow gas flows across otherwise barren expanses. Astronomers continue searching for observational evidence of these hidden bridges. Detecting them directly remains extremely difficult because dark matter emits no light. Yet subtle gravitational effects and gas distributions hint that the web extends even into the loneliest regions of the cosmos. The universe never becomes completely disconnected. Another remarkable fact concerns galaxy formation along filaments. Studies show galaxies near cosmic filaments often contain enhanced gas supplies and higher star formation rates compared to more isolated systems. Filaments appear to funnel material toward galaxies continuously, feeding their growth across cosmic time. These structures behave almost like circulatory systems for the universe. Gas flows inward. Galaxies grow. Stars form. Black holes feed. Energy spreads outward again. The cosmic web is not static architecture. It is dynamic and alive with motion. Another fascinating discovery involves the temperature of gas inside filaments. While galaxy clusters contain extremely hot, dense gas, filament gas exists at lower densities and temperatures ranging from thousands to millions of degrees. Much of this material remains nearly invisible except through subtle absorption effects in distant quasar light. Astronomers sometimes call these regions the cosmic fog. Though diffuse, this intergalactic medium contains enormous amounts of matter spread across incomprehensible distances. One extraordinary observation came from studies using the Hubble Space Telescope. By examining ultraviolet light from distant quasars, astronomers detected absorption signatures from tenuous hydrogen gas stretching along cosmic filaments. The findings confirmed predictions made decades earlier by cosmological simulations. The hidden web truly exists. Another remarkable fact is that the web influences galaxy shape and evolution over billions of years. Galaxies falling into dense clusters through filaments often experience gravitational interactions, gas stripping, and star formation changes as their environments evolve. A galaxy's location within the web helps determine its future. Dense nodes produce crowded, chaotic histories, Void regions produce quieter, isolated evolution. Filaments create transitional environments connecting both extremes. The architecture of the universe shapes the destinies of galaxies themselves. Another deeply fascinating phenomenon involves cosmic shocks. As gas flows through filaments toward clusters, enormous shock waves can form where material collides and compresses. These shocks heat intergalactic gas and accelerate particles across gigantic distances. The cosmic web contains weather on scales beyond imagination. Invisible storms crossing millions of light years. Astronomers also discovered that supermassive black holes influence the web surrounding them. Energetic jets from active galactic nuclei can inject heat and magnetic energy into intergalactic space, affecting gas distributions far beyond their host galaxies. The relationship between galaxies and the web is therefore two-way. The web shapes galaxies. Galaxies reshape the web. Another extraordinary fact concerns the future evolution of the cosmic web itself. Dark energy is accelerating cosmic expansion, gradually increasing separation between large-scale structures. Over trillions of years, distant filaments and clusters will move beyond observable horizons entirely. The web will slowly fragment. Galaxies gravitationally bound together will remain connected locally, but enormous voids between structures will continue expanding. Future observers may see only their local galactic group surrounded by darkness. Most evidence of the cosmic web may eventually disappear from view. In a profound sense, humanity lives during one of the best eras in cosmic history for observing the large-scale structure of the universe. Another remarkable discovery involves alignment across enormous distances. Some studies suggest quasars and galaxies may exhibit unexpected large-scale orientation patterns relative to cosmic filaments. While debates continue regarding interpretation, such observations hint that the geometry of the universe may influence structures over astonishing scales. The cosmos appears more interconnected the deeper scientists investigate. Another fascinating aspect is how simulations recreate the web with extraordinary realism. Modern supercomputers model billions of particles representing dark matter and gas evolving under gravity across cosmic time. The resulting structures closely resemble actual observations from galaxy surveys. Filaments emerge naturally. Voids expand naturally. Clusters form naturally. The universe's immense complexity arises from relatively simple physical laws operating patiently across billions of years. There's something deeply calming about that idea. Order emerging slowly from simplicity. Another curious fact is that some galaxies seem almost suspended between voids and filaments, occupying transitional environments where matter density changes dramatically over relatively short cosmic distances. These galaxies provide valuable clues about how environment influences star formation, gas retention, and long-term evolution. Astronomers continue mapping these regions carefully because they reveal how galaxies adapt while moving through the cosmic web. And perhaps the most beautiful truth of all is this: the universe is not random chaos scattered across empty space. It is connected. Every galaxy belongs to larger structures. Every filament links distant regions together. Every void helps define the shape surrounding it. The cosmos resembles a vast living tapestry woven from gravity, dark matter, gas, radiation, and time itself. Far beyond Earth, beyond the Milky Way, beyond visible stars, invisible threads stretch across unimaginable darkness, connecting the galaxies together. And drifting silently between those threads lie the great cosmic voids, immense oceans of emptiness giving shape to the hidden web of the universe. Chapter 7: Supervoids, Dark Matter, and Cosmic Mysteries. Some mysteries in the universe are hidden inside brilliant explosions. Others hide inside black holes. And some of the greatest mysteries of all hide inside emptiness itself. Cosmic voids already stretch human imagination beyond ordinary understanding. But among them exist even larger and stranger structures known as supervoids. Enormous regions of space so vast and underdense that they influence ancient light, galactic motion, and perhaps even humanity's understanding of the universe itself. These are among the largest known structures in existence. And despite decades of research, scientists still do not fully understand them. One of the first astonishing facts about supervoids is their unimaginable scale. Ordinary cosmic voids may span tens of millions of light years. Supervoids, however, can stretch across hundreds of millions of light years, containing far fewer galaxies than average across those enormous volumes. Some are so large that if the Milky Way galaxy were placed inside one, nearby major galaxies might become almost invisible to the naked eye even through advanced telescopes. The universe itself would appear dramatically emptier. One famous example is the Eridanus supervoid, often associated with a mysterious cold spot in the cosmic microwave background. This giant underdense region may extend over 1 billion light years across, depending on how its boundaries are measured. The scale is almost impossible to visualize. Light itself requires hundreds of millions of years simply to cross these structures. Another remarkable fact is that supervoids may help scientists study dark matter more effectively than crowded galaxy clusters. Dark matter remains one of the deepest unsolved mysteries in physics. It cannot be seen directly because it neither emits nor absorbs light. Yet its gravitational influence shapes galaxies, filaments, and the large-scale structure of the universe. Supervoids provide unique environments for examining dark matter behavior because they contain relatively little ordinary matter to complicate observations. In crowded regions, many overlapping gravitational interactions occur simultaneously. Inside supervoids, the simpler environment allows subtle effects to stand out more clearly. The emptiest places may reveal the invisible structure underlying reality itself. Another fascinating fact is that supervoids are not perfectly empty. Even within these enormous underdense regions, faint galaxies, diffuse gas, dark matter, and radiation continue to exist. In fact, simulations suggest supervoids contain delicate hidden structures, faint filaments and sparse galaxy chains stretching through darkness like ghostly remnants of the cosmic web. The universe seems incapable of producing perfect nothingness. One especially mysterious phenomenon involves how supervoids affect ancient light from the Big Bang. As photons cross giant underdense regions, evolving gravitational conditions slightly alter their energy. This contributes to the integrated Sachs-Wolf effect, where cosmic microwave background photons gain or lose tiny amounts of energy while traveling through large-scale structures. Supervoids amplify this process due to their immense size. This is why astronomers became so interested in the cold spot anomaly. Some researchers proposed that a giant supervoid along the line of sight could partially explain why a region of the cosmic microwave background appears colder than expected. Though debate continues, the idea demonstrated how giant voids might leave fingerprints on the oldest observable light in the universe. Another extraordinary fact is that supervoids continue expanding over time. Matter gradually flows outward from underdense regions toward surrounding filaments and clusters, causing supervoids to become larger and emptier as billions of years pass. This process sharpens the contrast between crowded and lonely regions of the cosmos. The rich regions grow richer. The empty regions grow emptier. Dark energy accelerates this trend further by driving the universe's expansion faster and faster. One especially curious discovery is that galaxies near supervoid edges sometimes exhibit coherent motion patterns. Because gravity pulls matter away from underdense centers toward denser surrounding regions, galaxies drift systematically relative to the void geometry. These flows span enormous distances. Entire galaxy groups participate in slow gravitational migrations lasting billions of years. Astronomers can measure these motions statistically, using them to test cosmological models describing dark matter and dark energy. Another fascinating fact involves the shape of supervoids. Unlike perfect spheres, many supervoids possess complex, irregular geometries influenced by surrounding structures. Some overlap with neighboring voids, forming giant interconnected regions. Others appear elongated or flattened, depending on the arrangement of nearby filaments and clusters. Defining where a supervoid truly begins or ends can become surprisingly difficult. The boundaries between emptiness and structure are gradual rather than sharp. Another remarkable aspect of supervoids is their potential role in testing modified gravity theories. Einstein's general relativity explains gravity extremely successfully across many situations. Yet certain cosmological mysteries, including dark matter and dark energy, have inspired alternative ideas suggesting gravity behaves differently on enormous scales. Some modified gravity theories predict effects that become especially noticeable inside low-density environments like supervoids. Because gravitational forces are weaker there, subtle deviations from standard predictions may emerge more clearly. This makes supervoids important laboratories for testing the foundations of physics itself. Another extraordinary fact concerns the rarity of massive galaxies inside deep supervoids. Traditional galaxy formation models predict that large galaxies should be uncommon in underdense environments because less matter is available for growth. Yet astronomers occasionally discover surprisingly large spiral galaxies existing within or near giant void regions. These galaxies challenge theoretical expectations. Some researchers suspect slow gas accretion along faint hidden filaments may allow isolated galaxies to grow gradually over billions of years despite their lonely surroundings. Others believe certain dark matter distributions stabilize galactic evolution in unexpected ways. The deeper scientists investigate supervoids, the more complicated the universe becomes. Another fascinating mystery involves neutrinos. Neutrinos are tiny, nearly massless particles flooding the universe in enormous numbers. Though difficult to detect, they influence cosmic structure formation because their high velocities smooth matter distributions across large scales. The growth and shapes of supervoids depend partly on neutrino behavior. By comparing observed supervoid structures to simulations, cosmologists can estimate limits on neutrino masses, one of the major unanswered questions in particle physics. Again, emptiness becomes a tool for understanding the smallest building blocks of nature. One especially calming thought emerges when imagining life inside a supervoid galaxy. The night sky there would feel profoundly different from humanity's own skies. Nearby galaxies would be far rarer. The cosmic web would appear distant and sparse. Deep space observations might reveal far less obvious structure. Civilizations growing up in such isolation could develop entirely different cosmological ideas. They might struggle to discover the true scale of the universe because fewer galaxies would surround them. Their cosmos would appear lonelier, quieter, more mysterious. Another extraordinary discovery is that supervoids dominate huge portions of cosmic volume despite containing relatively little matter. Most visible matter in the universe concentrates along filaments and clusters, yet most actual space consists of vast underdense regions. The universe is shaped more by emptiness than by matter. And those empty regions continue influencing light, gravity, motion, and cosmic evolution across unimaginable distances. Far beyond crowded galaxy clusters, beneath ancient photons crossing billions of years of darkness, supervoids drift silently through the universe. Immense cosmic oceans hiding clues about dark matter, dark energy, gravity, and the ultimate fate of reality itself. The more humanity studies the universe, the more it becomes clear that most of reality is invisible. Stars, planets, nebulae, and galaxies may appear spectacular through telescopes, but they represent only a tiny fraction of the cosmos. Beneath everything visible lies an unseen framework of dark matter and dark energy shaping the universe on the largest scales. And nowhere are these hidden forces more mysterious than inside the great supervoids. One of the most astonishing facts in modern cosmology is that ordinary matter, the matter forming stars, planets, oceans, and living beings, accounts for less than 5% of the universe. Roughly 27% appears to consist of dark matter, while nearly 68% exists as dark energy. Humanity lives inside a universe mostly made of unknown things. Supervoids help scientists investigate both. Another fascinating fact is that dark matter behaves differently from ordinary matter because it interacts primarily through gravity. It does not emit light, absorb light, or appear directly in telescopes. Yet its presence becomes obvious through gravitational effects. Galaxies rotate too quickly for visible matter alone to hold them together. Galaxy clusters contain more gravity than observable matter can explain. The cosmic web itself forms patterns requiring vast amounts of unseen mass. Dark matter provides the missing gravitational scaffolding. Inside supervoids, dark matter densities remain lower than average, but not zero. Simulations suggest diffuse dark matter still stretches across these enormous regions, forming faint structures difficult to detect directly. Some researchers compare it to invisible fog permeating cosmic emptiness. Another extraordinary fact involves weak gravitational lensing. Gravity bends light traveling through space. Massive galaxy clusters create strong lensing effects capable of magnifying distant galaxies dramatically. Supervoids, however, create the opposite effect. Their lower matter density slightly reduces gravitational focusing. This causes tiny distortions in the shapes and brightness of distant galaxies viewed through supervoid regions. Although extremely subtle, astronomers can detect these patterns statistically across enormous galaxy surveys. Even emptiness bends light. And through those distortions, scientists can map hidden dark matter distributions inside the voids themselves. Another remarkable mystery concerns dark energy. Dark energy appears responsible for accelerating cosmic expansion, yet nobody fully understands what it actually is. Some theories describe it as a property of empty space itself. Others suggest entirely new physics may be involved. Supervoids are especially sensitive to dark energy, because they expand faster than denser regions of the universe. As dark energy drives cosmic acceleration, matter evacuates voids more efficiently over time. Measuring how supervoids grow and evolve, therefore, provides important clues about the behavior of dark energy across cosmic history. The largest empty regions in existence may help explain the fate of the universe. Another fascinating phenomenon involves cosmic flows. Galaxies do not merely move outward due to expansion. They also experience additional motions caused by gravitational attraction from surrounding structures. Giant supervoids contribute significantly to these motions by creating large-scale imbalances in matter distribution. Galaxies near void boundaries gradually drift away from underdense regions toward denser clusters and filaments. These motions occur slowly across billions of years, but can span enormous cosmic distances. Entire galaxy superclusters participate in these gravitational migrations. One especially mysterious structure connected to these flows is the Great Attractor, a massive concentration of matter influencing galaxy motion across hundreds of millions of light years. Nearby voids may also contribute to these large-scale motions by shaping gravitational gradients across space. The universe behaves like an enormous interconnected gravitational landscape. Another extraordinary fact is that supervoids may preserve ancient cosmological information better than crowded regions. In dense galaxy clusters, repeated mergers and energetic processes erase delicate early structures over time. But inside quieter, underdense regions, subtle features from earlier cosmic epochs may survive more clearly. This makes supervoids valuable laboratories for studying primordial conditions. Some astronomers even investigate whether certain anomalies in large-scale cosmic structure hint at unknown physics from the earliest moments after the Big Bang. Another deeply fascinating mystery involves the possibility of hidden particles beyond current physics models. Some alternative dark matter theories predict additional particle interactions or exotic behaviors that might influence structure formation subtly inside low-density environments like supervoids. For example, warm dark matter models suggest dark matter particles possess slightly higher velocities than standard cold dark matter theories predict. This would suppress the formation of smaller structures inside voids differently than current models expect. Observing faint dwarf galaxies inside supervoids may therefore help distinguish between competing theories. Again, emptiness becomes an experimental laboratory on cosmic scales. Another remarkable fact concerns radio astronomy. Although supervoids contain relatively little matter, radio telescopes sometimes detect faint emissions and absorption signals from diffuse hydrogen gas crossing these regions. Upcoming observatories like the Square Kilometer Array are expected to map these structures with unprecedented sensitivity. Scientists hope these observations will reveal hidden filaments, dark matter distributions, and gas flows previously impossible to detect. The invisible universe may soon become clearer than ever before. Another curious mystery is whether supervoids influence the apparent expansion rate of the universe locally. Modern measurements of the Hubble constant, the rate of cosmic expansion, produce slightly conflicting results depending on the methods used. Some researchers propose that living near a relatively underdense region could subtly affect certain observations. Although supervoids alone likely cannot fully resolve the so-called Hubble tension, they may contribute small corrections important for precision cosmology. The place humanity occupies within the cosmic web matters more than scientists once realized. Another extraordinary idea connected to supervoids involves the ultimate future of cosmic structure. As dark energy continues accelerating expansion, galaxies outside local gravitational groups will gradually disappear beyond observable horizons. Over unimaginable timescales, the universe will become increasingly fragmented into isolated islands surrounded by darkness. Future civilizations may inhabit galaxies drifting alone inside effectively endless voids. Most evidence of a larger cosmic web may eventually vanish from view. In that distant future, astronomy itself could become profoundly limited. Observers might see only their local galaxy group, while the rest of the universe recedes forever beyond detectable distance. Supervoids today provide glimpses into that future loneliness. Another fascinating fact is that some simulations suggest supervoids may eventually merge into even larger underdense regions over trillions of years. As cosmic expansion stretches space further, the contrast between clustered matter and empty space increases dramatically. The universe slowly evolves toward greater isolation. And yet, even in those immense, lonely expanses, galaxies will continue forming stars for vast stretches of time. Planetary systems will still exist. Ancient suns will still rise over unseen worlds. The cosmos remains alive even inside its deepest darkness. Perhaps the most haunting truth about supervoids is what they reveal about humanity's place in existence. Earth feels large to human beings. The solar system feels enormous. The Milky Way already surpasses ordinary imagination. Yet supervoids dwarf all familiar scales so completely that even entire galaxy clusters become tiny details within their vast emptiness. And still, those giant regions are essential parts of the universe's design. They shape the cosmic web. They influence ancient light. They reveal hidden dark matter. They help scientists investigate dark energy and gravity itself. Most importantly, they remind humanity that emptiness is not absence. Even the darkest regions of the cosmos carry structure, motion, history, and mystery beyond anything human civilization has fully understood. Far beyond crowded galaxies and brilliant nebulae, the giant supervoids drift silently through space. Enormous oceans of near emptiness shaping the destiny of the universe itself. Chapter 8. What void galaxies reveal about the fate of the universe. The universe is changing. Slowly, silently, relentlessly. Every galaxy, every star, every drifting cloud of gas exists within a cosmos that has been evolving for nearly 13.8 billion years. The structures humanity sees today, galaxies woven through the cosmic web, immense clusters glowing with billions of suns, and gigantic voids stretching across unimaginable darkness, are only temporary chapters in a much longer story. And strangely enough, some of the clearest clues about the universe's ultimate fate come not from crowded galaxy clusters, but from the lonely void galaxies drifting through cosmic emptiness. One of the most profound facts about cosmic voids is that they grow larger over time. This process began shortly after the Big Bang, when tiny density fluctuations shaped the early universe. Regions containing slightly more matter gradually attracted additional material through gravity, eventually forming galaxies and clusters. Meanwhile, underdense regions lost matter to their surroundings. The rich regions became richer. The empty regions became emptier. And across billions of years, cosmic voids expanded into enormous silent oceans surrounding the cosmic web. This trend continues even now. As dark energy accelerates the expansion of the universe, voids grow increasingly dominant. In a sense, the future belongs to emptiness. Another extraordinary fact is that the observable universe already contains galaxies moving away from humanity faster and faster due to cosmic expansion. Distant galaxies are not traveling through space in the ordinary sense. Instead, space itself is stretching between them. The farther away a galaxy lies, the faster it appears to recede. And dark energy amplifies this process continuously. Eventually, many galaxies currently visible from Earth will disappear beyond observable horizons entirely. Light emitted from them will never again reach the Milky Way. This realization transformed cosmology profoundly. The universe is not static. It is becoming more isolated over time. Void galaxies provide living previews of that distant future. Inside giant cosmic voids, galaxies already exist in relative isolation. Some have few nearby neighbors within tens of millions of light years. Civilizations evolving there, if any exist, might witness skies far emptier than humanity's own. In the far future of the universe, many galaxies everywhere may experience similar isolation. Another fascinating fact involves the local group, the galactic neighborhood containing the Milky Way galaxy and the Andromeda Galaxy. These galaxies are gravitationally bound together, meaning cosmic expansion will not separate them completely. Instead, they will eventually collide and merge several billion years from now, forming a larger galaxy, sometimes nicknamed Milkomeda. But beyond the local group, distant galaxies will continue receding. Over trillions of years, most of the observable cosmic web may disappear from view entirely. Future astronomers living inside merged galactic remnants could struggle to discover the true history of the universe because evidence of large-scale expansion would become inaccessible. The cosmos itself may hide its own origins with time. Another remarkable fact is that stars will not shine forever. Galaxies slowly consume their supplies of hydrogen gas, the raw material required for star formation. In crowded galaxy clusters, collisions and black hole activity accelerate these changes. But inside isolated void galaxies, star formation may continue gently for much longer periods due to preserved gas reservoirs and fewer disruptive interactions. Void galaxies may become some of the last actively star-forming systems in the distant future universe. Their quiet isolation allows them to evolve more slowly. Another deeply fascinating concept connected to cosmic fate is heat death. According to current cosmological understanding, the universe may continue expanding forever. Over unimaginable timescales, stars will exhaust their fuel, galaxies will darken, and matter itself may gradually decay, depending on the laws of particle physics. Eventually, the cosmos could approach a state of maximum entropy, a condition where usable energy becomes extremely scarce. No bright new stars, no energetic structures forming. Only cold, isolated remnants drifting through darkness. Cosmic voids already resemble early stages of this future condition. Vast expanses of near emptiness. Lonely galaxies separated by immense distances. Silent darkness dominating most of space. Another extraordinary fact is that dark energy appears to grow increasingly important over time. In the early universe, matter dominated cosmic dynamics. Gravity slowed expansion somewhat because galaxies and dark matter pulled inward. But as the universe expanded and matter spread thinner, dark energy gradually became dominant. Today, dark energy controls the large-scale future of cosmic expansion. And because voids contain relatively little matter, they respond strongly to its influence. Some cosmologists describe voids as magnifying glasses for studying dark energy. Their growth rates reveal how cosmic acceleration behaves across billions of years. Another fascinating possibility involves the Big Rip hypothesis. Most evidence currently supports a universe expanding forever at a stable accelerating rate. But some speculative models suggest dark energy could strengthen over time. If that occurred, expansion might eventually become so extreme that galaxies, stars, planets, and even atoms themselves would be torn apart. This catastrophic scenario remains highly uncertain. Yet if it were true, cosmic voids would play central roles because expansion already dominates strongly inside them. The emptiest regions would become even emptier faster than anywhere else. Another remarkable fact is that black holes may outlive ordinary stars by unimaginable spans of time. Long after star formation ends, black holes could remain among the last major structures in existence. Yet even black holes are not eternal according to modern physics. Through a quantum process called Hawking radiation, they may slowly evaporate across incomprehensible timescales. The final black holes could survive for numbers of years, so enormous they barely fit within human mathematics. And still, beyond them, the voids would remain. Another curious discovery is that isolated galaxies may preserve information about ancient cosmic conditions longer than crowded galaxies. In dense environments, repeated mergers erase delicate structures over time. But quiet void galaxies evolve more gently, potentially retaining ancient dynamical patterns across billions of years. They are cosmic archives drifting through darkness. Astronomers continue studying them carefully because they reveal not only the universe's past, but also its future trajectory. Another calming thought emerges when imagining the far future cosmos. Even if the universe becomes increasingly dark and isolated, stars will continue shining for astonishingly long periods. Red dwarf stars, the smallest and longest-lived stars, may survive for trillions of years, vastly longer than the Sun. Planets around such stars could remain illuminated long after many brighter stars disappear. Life, perhaps somewhere, may continue enduring quietly inside lonely galaxies surrounded by darkness. The universe evolves slowly. Another extraordinary fact is that cosmic voids occupy most of the universe's volume already. Galaxies and clusters contain much of the visible matter, but emptiness dominates space itself. And as expansion continues, that dominance will grow. The future universe may resemble a vast collection of isolated galactic islands surrounded by enormous silent oceans of darkness. Void galaxies are previews of that coming age. Far beyond crowded clusters and brilliant nebulae, they drift quietly through expanding emptiness. Lonely lanterns carrying clues about the destiny of the cosmos itself. Far in the future, the night sky may become almost empty. Not because stars stop existing immediately, not because galaxies suddenly vanish, but because the universe itself keeps expanding, stretching the distances between cosmic structures farther and farther apart until most galaxies disappear beyond observable horizons forever. This is the destiny modern cosmology currently suggests. And strangely, humanity can already glimpse that future by studying the isolated galaxies drifting through cosmic voids today. One of the most extraordinary facts about the future universe is that cosmic expansion is accelerating rather than slowing down. When astronomers first discovered this in the late 1990s through observations of distant supernovae, the results shocked the scientific world. Gravity was expected to slow expansion gradually over time. Instead, the universe appeared to be speeding up. Something mysterious, now called dark energy, was overpowering gravity on the largest scales. And cosmic voids became crucial to understanding this phenomenon because their low-density environments respond especially strongly to accelerated expansion. The emptiest places in the universe reveal its fastest growing behavior. Another remarkable fact is that future civilizations may lose access to evidence of the Big Bang entirely. Today, astronomers can observe the cosmic microwave background, distant galaxies, and large-scale expansion. But over trillions of years, cosmic expansion will stretch microwave radiation into wavelengths too large to detect easily. Distant galaxies will move beyond observable reach. Future observers living inside isolated galactic remnants may see only a dark, empty universe surrounding them. Without evidence of expansion or the cosmic web, they might never discover that the universe once contained countless galaxies spread across enormous structures. In a profound sense, humanity lives during a privileged era of cosmic visibility. The universe currently reveals its history to us. Another fascinating fact is that void galaxies may continue forming stars long after crowded galaxies become inactive. Their preserved hydrogen reservoirs and low interaction rates allow gentle star formation to persist over extremely long periods. While massive galaxies exhaust their gas through mergers and energetic activity, isolated void systems evolve more slowly and quietly. They may become some of the final islands of ongoing stellar birth in the far future universe. The loneliest galaxies may also become the longest lived. Another extraordinary concept connected to cosmic destiny is proton decay. Some theories in particle physics suggest protons, the particles forming atomic nuclei, may eventually decay over unimaginable timescales. If true, ordinary matter itself would slowly dissolve into radiation and subatomic particles across periods vastly exceeding the current age of the universe. No experiment has confirmed proton decay yet, but if it occurs, even planets, stars, and galaxies would eventually disintegrate, and still the voids would remain, growing larger as the universe expanded. Another deeply mysterious possibility involves vacuum decay. According to certain interpretations of quantum field theory, the universe may exist in a metastable state, not the lowest possible energy configuration. In theory, a quantum event could someday trigger a transition to a lower energy vacuum state spreading outward at the speed of light. Such an event would fundamentally alter the laws of physics themselves. Atoms might no longer remain stable. Matter could cease existing in familiar forms. Fortunately, there is no evidence suggesting such a catastrophe is imminent. Yet the possibility reveals how cosmic fate may depend on physics humanity still barely understands. Another fascinating fact is that black holes could dominate the universe for incomprehensibly long eras after ordinary stars disappear. During the so-called black hole era, galaxies would mostly contain stellar remnants, dead stars, and slowly evaporating black holes. Hawking radiation predicts black holes emit tiny amounts of energy due to quantum effects near their event horizons. Over immense timescales, even supermassive black holes eventually evaporate. A giant black hole containing billions of solar masses might survive for numbers of years so vast they exceed ordinary imagination completely. And beyond those unimaginable eras, darkness would continue expanding through the voids. Another remarkable fact is that cosmic structure itself gradually freezes over time. Today, galaxies still merge, clusters still evolve, and matter still flows along the cosmic web. But accelerating expansion increasingly isolates gravitationally bound systems from one another. Eventually, only local galaxy groups will remain connected. The larger cosmic web will effectively dissolve from observable reality. Void galaxies today offer previews of that isolation. Their quiet environments resemble the conditions future galaxies may experience almost everywhere. Another deeply calming thought emerges from this long-term vision of the universe. Even in extreme isolation, stars can continue shining for astonishingly long periods. Red dwarf stars may burn slowly for trillions of years, providing stable energy to orbiting worlds far longer than larger stars like the Sun. If life exists elsewhere in the universe, some civilizations may survive deep into these distant cosmic ages within quiet, isolated galaxies. The future universe may not be crowded or brilliant, but may still contain light. Another extraordinary fact involves the ultimate dominance of entropy. Over time, usable energy becomes increasingly spread out and unavailable for complex processes. This gradual movement toward thermodynamic equilibrium defines the long-term direction of cosmic evolution. Voids embody this tendency beautifully. They grow larger. Matter becomes more isolated. Energy disperses across expanding space. The universe slowly drifts toward greater stillness. And yet even this immense process unfolds across timescales almost impossible to comprehend. Another fascinating possibility concerns artificial civilizations in the far future. Some physicists and philosophers speculate that advanced civilizations might attempt to survive cosmic expansion by gathering stars, harvesting black hole energy, or migrating toward gravitationally bound galaxy clusters before isolation becomes complete. Whether such civilizations could truly resist cosmic evolution remains unknown, but the idea itself reveals how deeply humanity has begun contemplating the future of the universe. Another remarkable truth is that cosmic voids dominate not only the universe's present structure, but likely its future appearance as well. Most of the cosmos already consists of enormous underdense regions. As expansion accelerates, those empty expanses will grow ever larger. The future universe will increasingly resemble a vast archipelago of isolated galaxies drifting through endless darkness. Void galaxies are the first ambassadors of that coming era. Another extraordinary realization is how temporary the current universe truly is. Human beings live during a period when stars actively form. Galaxies remain visible across billions of light years, and cosmic structure appears rich and vibrant. This age of cosmic illumination will not last forever. The universe has seasons, and humanity exists during one of its brightest chapters. Perhaps the most haunting and beautiful fact of all is that even the emptiest regions of the cosmos still contain history. Ancient photons from the Big Bang continue crossing the voids. Dark matter still shapes invisible structure. Lonely galaxies still rotate beneath dark skies. Stars still rise over unseen planets orbiting silent suns. The universe remains alive even in its deepest solitude. And through the study of void galaxies, humanity has learned something profound. Emptiness is not the absence of meaning. It is part of the design. The giant cosmic voids surrounding the galaxies are not mistakes in the universe. They shape the cosmic web, preserve ancient conditions, reveal the influence of dark matter and dark energy, and offer glimpses into the ultimate destiny awaiting the cosmos itself. Far beyond the crowded brilliance of galaxy clusters, Lonely galaxies drift through silent oceans of darkness, carrying within them the story of where the universe came from and where it may one day go.